Welcome to our full and free tutorial about statistics. We will uncover the tools and techniques that help us make sense of data. This video is designed to guide you through the fundamental concepts and most powerful statistical tests used in research today. From the basics of descriptive statistics to the complexities of regression and beyond, we'll explore how each method fits into the bigger picture of data analysis. And don't worry, if you have no clue about statistics, we'll go through everything step by step. If you like, you can find all topics in our book as well. The link is in the video description. So what is the outline of the video? Our video has 3 major parts. In the first part, we discuss what statistics is and what the differences between descriptive and inferential statistics are. In the second part, we go through the most common hypothesis tests like t-test and ANOVA. And we discuss the differences between parametric and non-parametric tests. And in the third part, we take a look at correlation analysis and regression analysis. And finally, we talk about cluster analysis. We have prepared detailed videos for each section. So let's start with the video that explains what statistics is. After this video, you will know what statistics is, what descriptive statistics is, and what inferential statistics is. So let's start with the first question. What is statistics? Statistics deals with the collection, analysis, and presentation of data. An example. We would like to investigate whether gender has an influence on the preferred newspaper. Then gender and newspaper are our so-called variables that we want to analyze. In order to analyze whether gender has an influence on the preferred newspaper, we first need to collect data. To do this, we create a questionnaire that asks about gender and preferred newspaper. We will then send out the survey and wait 2 weeks. Afterwards, we can display the received answers in a table. In this table, we have 1 column for each variable, 1 for gender and 1 for newspaper. On the other hand, each row is the response of 1 surveyed person. The first respondent is male and stated New York Post. The second is female and stated USA Today, and so on and so forth. Of course, the data does not have to be from a survey. The data can also come from an experiment in which you, for example, want to study the effect of 2 drugs on blood pressure. Now the first step is done. We have collected data and we can start analyzing the data. But what do we actually want to analyze? We did not survey the entire population, but we took a sample. Now the big question is, do we just want to describe the sample data, or do we want to make a statement about the whole population? If our aim is limited to the sample itself, i.e. we only want to describe the collected data, we will use descriptive statistics. Descriptive statistics will provide a detailed summary of the sample. However, if we want to draw conclusions about the population as a whole, inferential statistics are used. This approach allows us to make educated guesses about the population based on the sample data. Let us take a closer look at both methods, starting with descriptive statistics. Why is descriptive statistics so important? Let's say a company wants to know how its employees travel to work, so the company creates a survey to answer this question. Once enough data has been collected, this data can be analyzed using descriptive statistics. But what is descriptive statistics? Descriptive statistics aims to describe and summarize a data set in a meaningful way. But it is important to note that descriptive statistics only describe the collected data without drawing conclusions about a larger population. Put simply, just because we know how some people from one company get to work, we cannot say how all working people of the company get to work. This is the task of inferential statistics, which we will discuss later. To describe data descriptively, we now look at the 4 key components: measures of central tendency, measures of dispersion, frequency tables, and charts. Let's start with the first one, measures of central tendency. Measures of central tendency are, for example, the mean, the median, and the mode. Let's first have a look at the mean. The arithmetic mean is the sum of all observations divided by the number of observations. An example. Imagine we have the test scores of 5 students. To find the mean score, we sum up all the scores and divide by the number of scores. The mean test score of these 5 students is therefore 86.6. What about the median? When the values in a dataset are arranged in ascending order, the median is the middle value. If there is an odd number of data points, the median is simply the middle value. If there is an even number of data points, the median is the average of the two middle values. It is important to note that the median is resistant to extreme values or outliers. Let's look at this example. No matter how tall the last person is, the person in the middle remains the person in the middle, so the median does not change. But if we look at the mean, it does have an effect on how tall the last person is. The mean is therefore not robust to outliers. Let's continue with the mode. The mode refers to the value or values that appear most frequently in a set of data. For example, if 14 people travel to work by car, 6 by bike, 5 walk and 5 take public transport, then car occurs most often and is therefore the mode. Great, let's continue with the measures of dispersion. Measures of dispersion describe how spread out the values in a dataset are. Measures of dispersion are, for example, the variance and standard deviation, the range, and the interquartile range. Let's start with the standard deviation. The standard deviation indicates the average distance between each data point and the mean. But what does that mean? Each person has some deviation from the mean. Now we want to know how much the persons deviate from the mean value on average. In this example, the average deviation from the mean value is 11.5 centimeters. To calculate the standard deviation, we can use this equation. Sigma is the standard deviation, n is the number of persons, xi is the size of each person, and x bar is the mean value of all persons. But attention, there are two slightly different equations for the standard deviation. The difference is that we have once 1 divided by n and once 1 divided by n minus 1. To keep it simple, if our survey doesn't cover the whole population, we always use this equation to estimate the standard deviation. Likewise, if we have conducted a clinical study, then we also use this equation to estimate the standard deviation. But what is the difference between the standard deviation and the variance? As we now know, the standard deviation is the quadratic mean of the distance from the mean. The variance now is the squared standard deviation. If you want to know more details about the standard deviation and the variance, please watch our video. Let's move on to range and interquartile range. It is easy to understand. The range is simply the difference between the maximum and minimum value. Interquartile range represents the middle 50% of the data. It is the difference between the first quartile, Q1, and the third quartile, Q3. Therefore, 25% of the values are smaller than the interquartile range, and 25% of the values are larger. The interquartile range contains exactly the middle 50% of the values. Before we get to the last 2 points, let's briefly compare measures of central tendency and measures of dispersion. Let's say we measured the blood pressure of patients. Measures of central tendency provide a single value that represents the entire dataset, helping to identify a central value around which data points tend to cluster. Measures of dispersion, like the standard deviation, the range, and the interquartile range, indicate how spread out the data points are, whether they are closely packed around the center or spread far from it. In summary, while measures of central tendency provide a central point of the dataset, measures of dispersion describe how the data is spread around the center. Let's move on to tables. Here we will have a look at the most important ones, frequency tables and contingency tables. A frequency table displays how often each distinct value appears in a dataset. Let's have a closer look at the example from the beginning. A company surveyed its employees to find out how they get to work. The options given were car, bicycle, walk, and public transport. Here are the results from 30 employees. The first answered car, the next walk, and so on and so forth. Now we can create a frequency table to summarize this data. To do this, we simply enter the 4 possible options, car, bicycle, walk, and public transport in the first column, and then count how often they occurred. From the table, it is evident that the most common mode of transport among the employees is by car, with 14 employees preferring it. The frequency table thus provides a clear and concise summary of the data. But what if we have not only 1 but 2 categorical variables? This is where the contingency table, also called crossstep, comes in. Imagine the company doesn't have 1 factory but 2, 1 in Detroit and 1 in Cleveland. So we also ask the employees at which location they work. If we want to display both variables, we can use a contingency table. A contingency table provides a way to analyze and compare the relationship between 2 categorical variables. The rows of a contingency table represent the categories of one variable, while the columns represent the categories of another variable. Each cell in the table shows the number of observations that fall into the corresponding category combination. For example, the first cell shows that car and Detroit were answered 6 times. And what about the charts? Let's take a look at the most important ones. To do this, let's simply use datadepth.net. If you like, you can load this sample dataset with the link in the video description, or you just copy your own data into this table. Here below you can see the variables distance to work, mode of transport, and site. Datadepth gives you a hint about the level of measurement, but you can also change it here. Now, if we only click on mode of transport, we get a frequency table, and we can also display the percentage values. If we scroll down, we get a bar chart and a pie chart. Here on the left, we can adjust further settings. For example, we can specify whether we want to display the frequencies or the percentage values, or whether the bars should be vertical or horizontal. If you also select site, we get a cross table here and a grouped bar chart for the diagrams. Here we can specify whether we want the chart to be grouped or stacked. If we click on distance to work and mode of transport, we get a bar chart where the height of the bar shows the mean value of the individual groups. Here we can also display the dispersion. We also get a histogram, a box plot, a violin plot, and a rainbow plot. If you would like to know more about what a box plot, a violin plot, and a rainbow plot are, take a look at my videos. Let's continue with inferential statistics. At the beginning, we briefly go through what inferential statistics is, and then I'll explain the 6 key components to you. So what is inferential statistics? Inferential statistics allows us to make a conclusion or inference about a population based on data from a sample. What is the population and what is the sample? The population is the whole group we're interested in. If you want to study the average height of all adults in the United States, then the population would be all adults in the United States. The sample is a smaller group we actually study, chosen from the population. For example, 150 adults were selected from the United States. And now we want to use the sample to make a statement about the population. And here are the 6 steps how to do that. Number 1, hypothesis. First, we need a statement, a hypothesis that we want to test. For example, we want to know whether a drug will have a positive effect on blood pressure in people with high blood pressure. But what's next? In our hypothesis, we stated that we would like to study people with high blood pressure. So our population is all people with high blood pressure in, for example, the US. Obviously, we cannot collect data from the whole population, so we take a sample from the population. Now we use this sample to make a statement about the population. But how do we do that? For this, we need a hypothesis test. Hypothesis testing is a method for testing a claim about a parameter in a population using data measured in a sample. Great, that's exactly what we need. There are many different hypothesis tests. And at the end of this video, I will give you a guide on how to find the right test. And of course, you can find videos about many more hypothesis tests on our channel. But how does a hypothesis test work? When we conduct a hypothesis test, we start with a research hypothesis, also called alternative hypothesis. This is the hypothesis we are trying to find evidence for. In our case, the research hypothesis is the drug has an effect on blood pressure. But we cannot test this hypothesis directly with a classical hypothesis test. So we test the opposite hypothesis, that the drug has no effect on blood pressure. But what does that mean? First, we assume that the drug has no effect in a population. We therefore assume that in general, people who take the drug and people who don't take the drug have the same blood pressure on average. If we now take a random sample and it turns out that the drug has a large effect in a sample, then we can ask how likely it is to draw such a sample or one that deviates even more if the drug actually has no effect. So in reality, on average, there is no difference in a population. If this probability is very low, we can ask ourselves, maybe the drug has an effect in the population. And we may have enough evidence to reject the null hypothesis that the drug has no effect. And it is this probability that is called the p-value. Let's summarize this in 3 simple steps. Number 1, the null hypothesis states that there is no difference in the population. Number 2, the hypothesis test calculates how much the sample deviates from the null hypothesis. Number 3, the p-value indicates the probability of getting a sample that deviates as much as our sample or one that even deviates more than our sample, assuming the null hypothesis is true. But at what point is the p-value small enough for us to reject the null hypothesis? This brings us to the next point, statistical significance. If the p-value is less than a predetermined threshold, the result is considered statistically significant. This means that the result is unlikely to have occurred by chance alone, and that we have enough evidence to reject the null hypothesis. This threshold is often 0.05. Therefore, a small p-value suggests that the observed data, our sample, is inconsistent with the null hypothesis. This leads us to reject the null hypothesis in favor of the alternative hypothesis. A large p-value suggests that the observed data is consistent with the null hypothesis, and we will not reject it. But note, there is always a risk of making an error. A small p-value does not prove that the alternative hypothesis is true. It is only saying that it is unlikely to get such a result or a more extreme when the null hypothesis is true. And again, if the null hypothesis is true, there is no difference in the population. And the other way around, a large p-value does not prove that the null hypothesis is true. It is only saying that it is likely to get such a result or a more extreme when the null hypothesis is true. So there are 2 types of errors which are called type 1 and type 2 error. Let's start with the type 1 error. In hypothesis testing, a type 1 error occurs when a true null hypothesis is rejected. So in reality, the null hypothesis is true, but we make the decision to reject the null hypothesis. In our example, it means that the drug actually had no effect. So in reality, there is no difference in blood pressure whether the drug is taken or not. The blood pressure remains the same in both cases. But our sample happened to be so far off the true value that we mistakenly thought the drug was working. And a type 2 error occurs when a false null hypothesis is not rejected. So in reality, the null hypothesis is false, but we make the decision not to reject the null hypothesis. In our example, this means the drug actually did work. There is a difference between those who have taken the drug and those who have not, but it was just a coincidence that the sample taken did not show much difference, and we mistakenly thought the drug was not working. And now I'll show you how DataTab helps you to find a suitable hypothesis test and of course calculates it and interprets the results for you. Let's go to datatab.net and copy your own data in here. We will just use this example dataset. After copying your data into the table, the variables appear down here. DataTab automatically tries to determine the correct level of measurement, but you can also change it up here. Now we just click on Hypothesis Testing and select the variables we want to use for the calculation of the hypothesis test. DataTab will then suggest a suitable test. For example, in this case, a chi-square test, or in that case, an analysis of variance. Then you will see the hypotheses and the results. If you're not sure how to interpret the results, click on Summary in Words. Further, you can check the assumptions and decide whether you want to calculate a parametric or a non-parametric test. Now we know the differences between descriptive and inferential statistics. Our next step is to take a closer look at inferential statistics and at choosing the appropriate hypothesis test. Which hypothesis test you can use depends on the level of measurement of your data. There are 4 levels of measurement: nominal, ordinal, interval, and ratio. And here is an easy explanation for you. In this video, we are going to explore the 4 levels of measurement: nominal, ordinal, interval, and ratio. Each level gives us important information about the variable and supports different types of statistical analysis. By the end of this video, you will know what the levels of measurement are, and especially you will understand why you need these levels. So whether you are analyzing survey data, optimizing business operations, or studying for a statistics exam, stay tuned. What are levels of measurement? Levels of measurement refer to different ways that variables can be quantified or categorized. If you have a dataset, then every variable in the dataset corresponds to one of the 4 primary levels of measurement. These levels are nominal, ordinal, interval, and ratio. In practice, interval and ratio data are often used to perform the same analysis. Therefore, the term metric level is used to combine these 2 levels. Why do you need levels of measurement? The level of measurement is crucial in statistics for several key reasons. It tells us how our data can be collected, analyzed, and interpreted. Here's why understanding these levels is so important. Different levels of measurement support different statistical analysis. For instance, mean and standard deviation are suitable for metric data. In some cases, it may be suitable for ordinal data, but only if you know how to interpret the results correctly. And it definitely makes no sense to calculate it for nominal data. The level of measurement also tells us which hypothesis tests are possible and determines the most effective type of data visualization. For example, bar charts are great for nominal data, while histograms are better suited for metric data. So each level provides different information and supports various types of statistical analysis. But attention, the level of measurement is mainly relevant at the end of the research process. However, the types of data to be collected and their format are determined at the beginning. Therefore, it is crucial to consider the level of measurement of the data from the start to ensure that the desired tests can be conducted at the end. So let's take a closer look at each level of measurement. What characterizes nominal variables? This is the most basic level of measurement. Nominal data can be categorized but it is not possible to rank the categories in a meaningful way. Examples of nominal variables are gender with the categories male and female, types of animals with, for example, the categories dog, cat, bird, or preferred newspaper. In all these cases, you can tell whether one value corresponds to the other, so you can distinguish the values, but it is not possible to put the categories in a meaningful order. An example. We would like to investigate whether gender has an influence on the preferred newspaper. Both variables are nominal. So when we create a questionnaire, we simply list the possible answers for both variables. Since there is no meaningful order for nominal variables, it usually does not matter in which order the categories are listed in the questionnaire. Then we can display the collected data in a table, where each row is a person with the respective answer. We can now use our data to create frequency tables or bar charts. But what about the ordinal level of measurement? Ordinal data can be categorized, and in comparison with nominal data, it is possible to have a meaningful ranking of the categories. But differences between ranks do not have a mathematical meaning. This means the intervals between the data points are not necessarily equal. Examples of ordinal variables are all kinds of rankings like first, second, third, satisfaction ratings, very unsatisfied, unsatisfied, neutral, satisfied, very satisfied, and levels of education, high school, bachelor's, master's. In a questionnaire, you could ask, how satisfied are you with your current job? In this case, we have these 5 possible options. The answers can be categorized and there is a logic order. That's why the variable satisfaction with the job is an ordinal variable. What about metric variables? Metric variables are the highest level of measurement. Metric data is like ordinal, but the intervals between values are equally spaced. This means that differences and sums can be formed meaningfully. Examples of metric variables are income, weight, age, and electricity consumption. If you ask for a metric variable in a questionnaire, there's usually just an input field in which the person directly enters the value, for example, age or body weight. Let's look at what we've learned so far using an example. Imagine you're conducting a survey in a school to understand how pupils get to school. Here are questions you might ask, each corresponding to a different level of measurement. The first question could be, what mode of transportation do you use to get to school? Bus, car, bicycle, walk. This is of course a nominal variable. The answers can be categorized, but there is no meaningful order. This means that bus is not higher than bicycle, walk is not higher than car, and so on and so forth. If you want to analyze the results of this question, you can count how many students use each mode of transportation and present it in a bar chart. Further, you can ask, how satisfied are you with your current mode of transportation? Choices might include very unsatisfied, unsatisfied, neutral, satisfied, very satisfied. This is of course an ordinal variable. You can rank the responses to see which mode of transportation ranks higher in satisfaction, but the exact difference between satisfied and very satisfied, for example, or other options isn't quantifiable. And the last question, how many minutes does it take you to get to school? Minutes to get to school is a metric variable. Here you can calculate the average time to get to school and use all standard statistical measures. We can visualize this data with a histogram showing the distribution of time to get to school and compare the different transportation modes. So, using nominal data, we can categorize and count responses, but cannot infer any order. Ordinal data allows us to rank responses, but not to measure precise differences between ranks. Metric data enables us to measure exact differences between data points. As already mentioned, metric level of measurement can be further subdivided into interval scale and ratio scale. But what is the difference between interval and ratio level? Let's look at an example. In a marathon, of course, the time of the marathon runners is measured. Let's say the first one took 2 hours and the last one finished the marathon in 6 hours. Here we can say that the fastest runner was 3 times as fast as the slowest. Or to put it the other way around, the slowest one took 3 times as long as the fastest one. This is possible because there is a true 0 point at the beginning of the marathon where all runners start from 0. In this case, we have ratio level of measurement. If, however, the stopwatch is forgotten to start at the beginning of the race and only the differences are measured, starting from the fastest runner, we don't have this true 0. Now the runners cannot be put in proportion. In this case, we can say how big the interval between the runners is. For example, the fastest runner is 4 hours faster than the slowest runner, but we cannot say that the fastest runner was 3 times as fast as the slowest. This is because we don't know the absolute values for both runners. We still have equal intervals. We can say things like runner B finished 1 hour after the fastest runner and runner C finished 1 hour and 45 minutes after the fastest runner. The time differences are measurable and meaningful. But since there is no true 0 point, we can say the fastest runner was X times as fast as the slowest runner. We only know how much later the other runners finished relative to the fastest runner, but not their total running times. And in this case, we have an interval level of measurement. In summary, while both interval and ratio scales have equal intervals and support similar operations like addition and subtraction, ratio scales have a true 0 point. 0 represents the absence of the quantity being measured. This allows meaningful multiplication and division. And now a little exercise to check whether everything is clear to you. First, we have states of the US, which is a nominal level of measurement. This means the data is used for labeling or naming categories without any quantitative value. In this case, the states are names with no inherent order or ranking. Next, we have product ratings on a scale from 1 to 5. This is an example of ordinal data. Here the numbers do have an order or rank. 5 is better than 1, but the intervals between the ratings are not necessarily equal. Moving on to religious confession. Like the states, this is also nominal. The categories here, such as different religions, are for categorization and do not imply any order. Next, we have CO2 emissions in the year, which is measured on a metric ratio scale. This level allows for the full range of mathematical operations, including meaningful ratios. 0 emissions mean no emissions at all. Then we have telephone numbers. Although telephone numbers are numeric, they are categorized as nominal. They are just identifiers with no numerical value for analysis. Care level of patients is another ordinal example. This might include levels such as low, medium, and high care, which indicate an order, but not the exact difference between these levels. Living space in square meters is measured on a ratio scale. Like CO2 emissions, 0 square meters mean there is no living space, and comparisons like double or half are meaningful. Lastly, we have job satisfaction on a scale from 1 to 4. This is ordinal data. It ranks satisfaction levels, but the difference between each level isn't quantified. Now we know what a level of measurement is, and we can go through the hypothesis tests that are most popular and discuss when to use which test. Let's start with the video on the most common hypothesis test, the t-test. See you in a moment. This video is about everything you need to know about the t-test. After this video you know what a t-test is and when you use it, what types of t-tests there are, what the hypotheses and the assumptions are, how a t-test is calculated, and how you interpret the results. Let's start with the first question. What is a t-test? The t-test is a statistical test procedure. And what does the t-test do? The t-test analyzes whether there is a significant difference between the means of two groups. For example, the two groups may be patients who received once drug A and once drug B. We would now like to know if there is a difference in blood pressure between these two groups. Now there are three different types of t-tests: the one-sample t-test, the independent samples t-test, and the paired samples t-test. When do we use a one-sample t-test? We use the one-sample t-test when we want to compare the mean of a sample with a known reference mean. Example: a chocolate bar manufacturer claims that its chocolate bars weigh an average of 50 grams. To check this, we take a sample of 30 bars and weigh them. The mean value of this sample is 48 grams. Now we can use a one-sample t-test to check if the mean of 48 grams is significantly different from the claimed 50 grams. When do we use the independent samples t-test? We use the t-test for independent samples when we want to compare the means of two independent groups or samples. We want to know if there is a significant difference between these means. Example: we would like to compare the effectiveness of two painkillers. We randomly divide 60 people into two groups. The first group receives drug A and the second group receives drug B. Using an independent t-test, we can now test whether there is a significant difference in pain relief between the two drugs. When do we use the paired samples t-test? We use the paired samples t-test to compare the means of two dependent groups. Example: we want to know how effective a diet is. To do this, we weigh 30 people before the diet and then weigh exactly the same people after the diet. Now we can look at the difference in weight between before and after for each subject. We can now use a paired samples t-test to test whether there is a significant difference. In a paired sample, the measurements are available in pairs. The pairs result, for example, from repeated measurements with the same people. Independent samples are made up of people and measurements that are independent of each other. Here's an interesting note. The paired samples t-test is very similar to the one-sample t-test. We can also think of the paired samples t-test as having one sample that was measured at two different times. We then calculate the difference between the paired values, giving us a value for one sample. The difference is once -5, once +2, once -1, and so on and so forth. Now we want to test whether the mean value of the difference just calculated deviates from a reference value, in this case 0. This is exactly what the one-sample t-test does. What are the assumptions for a t-test? Of course, we first need a suitable sample. In the one-sample t-test, we need a sample and a reference value. In the independent t-test, we need two independent samples. And in the case of a paired t-test, a paired sample. The variable for which we want to test whether there is a difference between the means must be metric. Examples of metric variables are age, body weight, and income. For example, a person's level of education is not a metric variable. In addition, the metric variable must be normally distributed in all three t-test variants. To learn how to test if your data is normally distributed, watch my video Test for Normal Distribution. In case of an independent t-test, the variances in the two groups must be approximately equal. You can check whether the variances are equal using Levene's test. For more information, watch my video on Levene's test. So, what are the hypotheses of the t-test? Let's start with the one-sample t-test. In the one-sample t-test, the null hypothesis is the sample mean is equal to the given reference value. So there is no difference, and the alternative hypothesis is the sample mean is not equal to the given reference value. What about the independent samples t-test? In the independent t-test, the null hypothesis is the mean values in both groups are the same, so there is no difference between the two groups. And the alternative hypothesis is the mean values in both groups are not equal, so there is a difference between the two groups. And finally, the paired samples t-test. In a paired t-test, the null hypothesis is the mean of the difference between the pairs is 0. And the alternative hypothesis is the mean of the difference between the pairs is not 0. So now we know what the hypotheses are. Before we look at how the t-test is calculated, let us look at an example of why we actually need a t-test. Let's say there is a difference in the length of study for a bachelor's degree between men and women in Germany. Our population is therefore made up of all graduates of a bachelor who have studied in Germany. However, as we cannot survey all bachelor graduates, we draw a sample that is as representative as possible. We now use the t-test to test the null hypothesis that there is no difference in the population. If there is no difference in the population, we will certainly still see a difference in study duration in the sample. It would be very unlikely that we drew a sample where the difference would be exactly 0. In simple terms, we now want to know at what difference, measured in the sample, we can say that the duration of study of men and women is significantly different. And this is exactly what the t-test answers. But how do we calculate a t-test? To do this, we first calculate the t-value. To calculate the t-value, we need two values. First, we need the difference between the means, and then we need the standard deviation from the mean. This is also known as the standard error. In the one-sample t-test, we calculate the difference between the sample mean and the known reference mean. S is the standard deviation of the collected data and n is the number of cases. S divided by the square root of n is then the standard deviation from the mean, which is the standard error. In the dependent samples t-test, we simply calculate the difference between the two sample means. To calculate the standard error, we need the standard deviation and the number of cases from the first and second sample. Depending on whether we can assume equal or unequal variance for our data, there are different formulas for the standard error. Read more about this in our tutorial on datatab.net. In a paired sample t-test, we only need to calculate the difference between the paired values and calculate the mean from that. The standard error is then the same as for a one-sample t-test. So what have we learned so far about the t-value? No matter which t-test we calculate, the t-value will be greater if we have a greater difference between the means. And the t-value will be smaller if the difference between the means is smaller. Further, the t-value becomes smaller when we have a larger dispersion of the mean. So, the more scattered the data, the less meaningful a given mean difference is. Now we want to use the t-test to see if we can reject the null hypothesis or not. To do this, we can now use the t-value in two ways. Either we read the critical t-value from a table, or we simply calculate the p-value from the t-value. We'll go through both in a moment. But what is the p-value? A t-test always tests the null hypothesis that there is no difference. So first we assume that there is no difference in the population. When we draw a sample, This sample deviates from the null hypothesis by a certain amount. The p-value tells us how likely it is that we would draw a sample that deviates from the population by the same amount or more than the sample we drew. Thus, the more the sample deviates from the null hypothesis, the smaller the p-value becomes. If this probability is very, very small, we can of course ask whether the null hypothesis holds for the population. Perhaps there is a difference. But at what point can we reject the null hypothesis? This border is called the significance level, which is usually set at 5%. So if there is only a 5% chance that we draw such a sample, or one that is more different, then we have enough evidence to assume that we reject the null hypothesis. And to put it simple, we assume that there is a difference, that the alternative hypothesis is true. Now that we know what the p-value is, we can finally look at how the t-value is used to determine whether or not the null hypothesis is rejected. Let's start with the path through the critical t-value, which you can read from a table. To do this, we first need a table of critical t-values, which we can find on datatab.net under Tutorials and t-distribution. Let's start with the two-tailed case. We'll briefly look at the one-tailed case at the end of this video. Here below, we see the table. First, we need to decide what level of significance we want to use. Let's choose a significance level of 0.05 or 5%. Then we look in this column at 1 minus 0.05, which is 0.95. Now we need the degrees of freedom. In the one-sample t-test and the paired samples t-test, the degrees of freedom are simply the number of cases minus 1. So if we have a sample of 10 people, there are 9 degrees of freedom. In the independent samples t-test, we add the number of people from both samples and calculate that minus 2 because we have 2 samples. Note that the degrees of freedom can be determined in a different way depending on whether we assume equal or unequal variance. So if we have a 5% significance level and 9 degrees of freedom, we get a critical t-value of 2.262. Now on the one hand, we've calculated a t-value with the t-test and we have the critical t-value. If our calculated t-value is greater than the critical t-value, we reject the null hypothesis. For example, suppose we calculate a t-value of 2.5. This value is greater than 2.262, and therefore the two means are so different that we can reject the null hypothesis. On the other hand, we can also calculate the p-value for the t-value we've calculated. If we enter 2.5 for the t-value and 9 for the degrees of freedom, we get a p-value of 0.034. The p-value is less than 0.05 and we therefore reject the null hypothesis. As a control, we copy the t-value of 2.262 here. We get exactly a p-value of 0.05, which is exactly the limit. If you want to calculate a t-test with datatab, you just need to copy your own data into this table, click on Hypothesis Test, and then select the variables of interest. For example, if you want to test whether gender has an effect on income, you simply click on the two variables and automatically get a t-test calculated for independent samples. Here below you can read the p-value. If you're still unsure about the interpretation of the results, you can simply click on Interpretation in Words. A two-tailed t-test for independent samples, equal variances assumed, showed that the difference between female and male with respect to the dependent variable salary was not statistically significant. Thus, the null hypothesis is retained. The final question now is, what is the difference between directed hypotheses and undirected hypotheses? In the undirected case, The alternative hypothesis is that there is a difference. For example, there is a difference between the salary of men and women in Germany. We don't care who earns more, we just want to know if there is a difference or not. In a directed hypothesis, we are also interested in the direction of the difference. For example, the alternative hypothesis might be that men earn more than women or women earn more than men. If we look at the t-distribution graphically, we can see that in the two-sided case we have a range on the left and a range on the right. We want to reject the null hypothesis if we are either here or there. With a 5% significance level, both ranges have a probability of 2.5%, together just 5%. If we do a one-tailed t-test, the null hypothesis is rejected only if we are in this range, or, depending on the direction which we want to test, in that range. With a 5% significance level, all 5% fall within this range. We have seen how the t-test is a powerful tool for comparing the means of two groups to determine if they differ significantly. But what if we extend our analysis to more than two groups? This is where analysis of variance or ANOVA comes into play. So let's get started with ANOVA. Hello and welcome. In this video, I explain to you what an analysis of variance, a so-called ANOVA, is and how you can calculate it. There are different types of analyses of variance. This video is about the one-way or single-factor analysis of variance without measurement repetitions. And that's where we start. The first question is, why do you need an analysis of variance at all? What does an analysis of variance do? An analysis of variance checks whether there are statistically significant differences between more than two groups. Therefore, the analysis of variance is the extension of the t-test for independent samples to more than two groups. When calculating an independent t-test, we looked at whether there is a difference, or more precisely a difference in means, between two independent groups. For example, if there is a difference in the salary of men and women. In this case, we have two groups, the men's group and the women's group. If we want to compare more than two independent groups, we use the analysis of variance. In case of the t-test, we used an independent t-test if the two groups or samples were independent. This is the case if one person in the first group has nothing to do with a person from the second group. Exactly the same now applies to the analysis of variance without repeated measures, except that here we have at least 3 independent samples. If we have more than 2 dependent samples, we would use an analysis of variance with repeated measures. Now let's look at an example. Let's say that as the founder of DataTab, I might be interested in whether there are differences in the age between people who use DataTab, SPSS or R. In order to do this, I take a sample of people who use statistical software and ask them which statistical software they use and how old they are. I've only compared 3 groups in this example. Of course, there could also be more groups. In order to analyze this example, I would now use an ANOVA. So the next question is, what is the research question I can answer with using an ANOVA? The research question is there a difference in the population between the different groups of the independent variable in relation to the dependent variable? The independent variable is the variable with the different categories. In our example, it is the statistics software used. Here we have the 3 groups, DataTab, SPSS and R. The dependent variable in our example is the age of the software users. We would like to know whether the groups of the independent variables have an influence on the dependent variable. Of course, the analysis of variance does not give us any information about the direction of the causal relationship.
But why is our research question about the population? Don't we just have a sample? Actually, we want to make a statement about the population. Unfortunately, in most cases, it is not possible to survey the whole population, and we can only draw a sample. The aim is to make a statement about the population based on our sample with the help of the analysis of variance. For our example, the question would be, is there a difference between the users of different statistical software solutions in terms of age? But what about the hypotheses? In the case of the analysis of variance, the null hypothesis is that there are no differences between the means of the individual groups. We have our individual groups of which we can calculate the mean in each case, and our null hypothesis is that there is no difference in the mean in the population. The alternative hypothesis H1 is that there is a difference between at least two group means. Therefore, our null hypothesis assumes that there is no difference, and the alternative hypothesis says that there is a difference. All well and good. Now we know what the null hypothesis is. But what does this mean graphically? How can one picture that vividly? Let's say we want to test whether there is a difference in salary between the three groups, Group 1, Group 2 and Group 3. The salary has some dispersion. Some people earn 400 euros a month, some 2,600 and others 6,000 euros a month. Thus, both in the population and in our sample, the salary is broadly distributed. Now the question is, where does this variation come from? And can we explain some of the variation by these three groups? So how much of the variation in salary can we explain by dividing the people into these three groups? In the extreme case, the result could be that the salary in Group 1 has this distribution, in Group 2 that distribution, and in Group 3 the distribution would look like this. In this case, the division into groups could explain a lot of variance in a variable salary. The result would be different in this case. Here, however, we could explain almost no variance by forming the three groups. Within the groups, the variance is almost the same as in the whole sample. Therefore, it does not matter whether we form the groups or not. The three groups have nearly no influence on the salary. If we now look at the variance within the groups, we can see that in this case we have very small variances within the groups. So within this group we have a very small variance. Within that group, we have a small variance, and also in the last group. On the other hand, the variance between the groups is very large because the mean values of the individual groups are very far apart. In the other case, we have a very large variance within the groups. However, the variance between the groups is very small, because the mean values of the groups are very close together. How can we calculate an ANOVA? There are two possibilities for the calculation. Either you use a statistics software like DataTab, or you calculate the analysis of variance by hand. Admittedly, no one will calculate the analysis of variance by hand, but the knowledge is very helpful to understand more precisely how an analysis of variance works. In this video, I show you how you can easily calculate an analysis of variance online with DataTab. To calculate an analysis of variance with DataTab, just visit datatab.net. You can find the link in the video description below. Then you copy your own data into this table and click on this tab. Under this tab, you will find a variety of hypotheses tests. Here below, you can see the variables you copied into the table. Depending on which variables you select, DataTab will calculate the appropriate hypothesis test. If you click on a metric variable and a nominal variable with at least 3 characteristics, Data calculates an analysis of variance. Here you can read the p-value. If you don't know exactly how to interpret the p-value, just get the summary in words above. Furthermore, you can check the assumptions of the analysis of variance here.
Now that we understand how ANOVA helps us compare means across multiple groups, let's take it a step further. ANOVA looks at one factor at a time, but what if our study involves more than one factor? This is where two-way ANOVA becomes essential. Two-way ANOVA allows us to not only explore the effects of each individual factor on our outcome, but also how these factors interact with each other. This gives us a deeper understanding of the dynamics within our data. Let's explore the two-way ANOVA. What is a two-way ANOVA? A two-way ANOVA is a statistical method used to test the effect of two categorical variables on a continuous variable. The categorical variables are the independent variables, for example, the variable drug type with drug A and B, and gender with female and male. And the continuous variable is the dependent variable, for example, the reduction in blood pressure. So, the two-way ANOVA is the extension of the one-way ANOVA. While a one-way ANOVA tests the effects of a single independent variable on a dependent variable, a two-way ANOVA tests the effects of two independent variables. The independent variables are called factors. But what is a factor? A factor is, for example, gender of a person with the levels male and female, type of therapy with therapy A, B, and C, or the field of study with medicine, business administration, psychology, and mathematics. In an analysis of variance, a factor is therefore a nominal variable. We use an ANOVA whenever we want to test whether these levels have an influence on the so-called dependent variable. You might want to test whether gender has an effect on salary, whether therapy has an effect on blood pressure, or whether field of study has an effect on length of study. Salary, blood pressure, and length of study will then be the dependent variables. In each of these cases, you test whether the factor has an effect on the dependent variable. Since you only have one factor in these cases, you would use a one-way ANOVA. Okay, you're right. In the first case, we have a variable with only two categories, so of course we would use the independent samples t-test. But when do we use a two-way ANOVA? We use a two-factor analysis of variance when we have a second factor and we want to know whether this factor also has an effect on the dependent variable. We would also like to know whether, in addition to gender, the highest level of education has an impact on salary. Or we would like to include gender in addition to type of therapy. Or in the third case, we would also like to know whether the university attended, in addition to the field of study, has an influence on the length of study. Now we don't have one factor in all three cases, but two factors in each case. And since we now have two factors, we use a two-way analysis of variance. So in a one-way ANOVA, we have one factor from which we create the groups. If the factor we are looking at has three levels, for example, three different types of drug, we will have three groups to compare. In the case of a two-way analysis of variance, the group results from the combination of the levels of the two factors. If we have one factor with three levels and one with two levels, we have a total of 6 groups to compare. But what kind of statements can we make with a two-way ANOVA? With the help of a two-way ANOVA, we can answer 3 things. Whether the first factor has an effect on the dependent variable, whether the second factor has an effect on the dependent variable, and whether there is an interaction effect between the two factors. But what about the hypotheses in a two-way ANOVA?
There are 3 null hypotheses and therefore also 3 alternative hypotheses. The first null hypothesis is there is no significant difference between the groups of the first factor. And the alternative hypothesis, there is a significant difference between the groups of the first factor. The second null hypothesis is there is no significant difference between the groups of the second factor. And the alternative hypothesis, there is a significant difference between the groups of the second factor. And the third null hypothesis reflects the interaction effect. One factor has no effect on the effect of the other factor. And the alternative hypothesis, at least one factor has an influence on the effect of the other factor. And what about the assumptions? For the test results to be valid, several assumptions must be met. Number 1. Normality. The data within the groups should be normally distributed, or alternatively, the residuals should be normally distributed. This can be checked with a quantile-quantile plot. Number 2. Homogeneity of variances. The variance of data in groups should be equal. This can be checked with the Levene's test. Number 3. Independence. The measurements should be independent, i.e. the measured value of one group should not be influenced by the measured value of another group. Number 4. Measurement level. The dependent variable should have a metric scale level. But how to calculate a two-way ANOVA? Let's look at the example from the beginning. We would like to know if drug type and gender have an influence on the reduction in blood pressure. Drug type has the 2 levels drug A and B, and gender has the 2 levels male and female. To answer the question, we collect data. We randomly assigned patients to the treatment combinations and measured the reduction in blood pressure after a month. For example, the first patient receives drug A, is male, and after 1 month a reduction in blood pressure of 6 was measured. Now let us answer the questions. Is there a main effect of drug type on the reduction in blood pressure? Is there a main effect of gender on the reduction in blood pressure? And is there an interaction effect between drug type and gender on the reduction in blood pressure? For the calculation, we can use either a statistical software like DataTab or do it by hand. First, I will show you how to calculate it with DataTab and how to interpret the results. At the end, I will show you how to calculate the ANOVA by hand and go through all the equations. To calculate a two-way ANOVA online, simply visit datatab.net and copy your data into this table. Then click on Hypothesis Test. Under this tab, you will find a lot of hypothesis tests, and depending on which variable you select, you will get an appropriate hypothesis test suggested. We want to know if drug type and gender have an influence on the reduction in blood pressure. So let's just click on all 3 variables. DataTab now automatically gives us a two-way ANOVA. We can read the 3 null and the 3 alternative hypotheses here. Afterwards, we get the descriptive statistics and the Levene test for equal variance. With the Levene test, we can check if the variances within the groups are equal. The p-value is greater than 0.05, so we assume equality of variance in the groups for this data. And here we see the results of the analysis of variance. We'll look at these in more detail in a moment. But if you don't know exactly how to interpret the results, you can also just click on Summary in Words. In addition, you can check here if the requirements for the analysis of variance are met at all. But now back to the results. Let's take a closer look at this table. The first row tests the null hypothesis whether drug type has an effect on the reduction in blood pressure. The second row tests whether gender has an effect on the reduction in blood pressure. And the third row tests if the interaction has an effect. You can read the p-value in each case right at the back here. Let's say we set the significance level at 5%.
If our calculated p-value is less than 0.05, the null hypothesis is rejected. And if the calculated p-value is greater than 0.05, the null hypothesis is not rejected. Thus, we see that all three p-values are greater than 0.05, and therefore we cannot reject any of the three null hypotheses. Therefore, neither the drug type nor gender have a significant effect on the reduction in blood pressure. And there's also no significant interaction effect. But what does an analysis of variance actually do? And why is the word variance in analysis of variance? In a two-way analysis of variance, the total variance of the dependent variable is divided into the variance that can be explained by factor A, the variance that can be explained by factor B, the variance of the interaction, and the error variance. Actually, SS is not the variance, but the sum of squares. We will discuss how to calculate the variance in this case in a moment. But how can I imagine that? The dependent variable has some variance. In our example, not everyone will have the same reduction in blood pressure. We now want to know if we can explain some of this variance by the variables drug type, gender, and their interaction. The part that we cannot explain by these three terms accumulates in the error. If the result looked like this, we would be able to explain almost all the variance by factors A and B and their interaction, and we would only have a very small proportion that could not be explained. This means that we can make a very good statement about the reduction in blood pressure by the variable drug type, sex, and interaction. In this case, it would be the other way round. Drug type, gender, and the interaction almost have no effect on the reduction in blood pressure, and it all adds up in the error. But how do we calculate the sum of squares, the F value and the P value? Here we have our data, once drug type with drug A and B, and once gender with male and female. So these individuals are, for example, all male and have been given drug A. First, we calculate the mean values we need. We calculate the mean value of each group, so male and drug A, that is 5.8, then male and drug B, that is 5.4, and we do the same for female. Then we calculate the mean value of all males and females and the mean value of drug A and B. Finally, we need the total mean. We can now start to calculate the sum of squares. Let's start with the total sum of squares. We do this by subtracting the total mean from each individual value, squaring the result, and adding up all the values. The total mean is 5.4, so we calculate 6 minus 5.4 squared plus 4 minus 5.4 squared to finally 3 minus 5.4 squared. So we get a sum of squares of 84.8. The degrees of freedom are given by n times p times q minus 1. N is the number of people in a group, in our case 5, and p and q are the number of categories in each of the factors. In both cases, we have two groups. The total variance is calculated by dividing the sum of squares by the degrees of freedom. So we get 4.46. Now we can calculate the sum of squares between the groups. For this, we calculate the group mean minus the total mean. So 5.8 minus 5.4 squared plus 5.4 minus 5.4 squared, and the same for these two values. We get 7.6. In this case, the degrees of freedom are 3, which gives us a variance of 2.53. Now we can calculate the sum of squares of factor A. A dash is the mean value of the categories of factor A. So we calculate 5.9 minus the total mean value and 4.9 minus the total mean value. This results in 5. Together with the degrees of freedom, we can now calculate the variance for factor A, which is 5. We do the same for factor B. In this case, we use the mean values of male and female, and we get the variance of 0.8. Now we can calculate the sum of squares for the interaction. We obtain this by calculating the sum of squares minus the sum of squares of A and B. The degrees of freedom result to 1. For the interaction, we get a variance of 1.8. Finally, we can calculate the sum of squares of the error. We subtract the mean value of each group from the respective group values. So, in this group, we subtract 5.8 from each individual value. In this group, we subtract 5.4. Here we subtract 6. And then we subtract 4.4. This gives us a sum of squares of 77.2. The degrees of freedom are 16, and we get a variance of 4.83. And now we calculate the F values. These are obtained by dividing the variance of factor A, B, or the interaction by the error variance. So we get the F value for factor A by dividing the variance of factor A by the error variance, which is equal to 1.04. We can now do exactly the same for FB and FAB. To verify, we get exactly the same values with data-tab: 1.04, 0.17 and 0.37. For the calculation of the p-value, you need the degrees of freedom and the F distribution. So with these three values, you can either read the critical p-value in a table, or as usual, you just use a software to calculate the p-values. You can find a table of critical F values on data-tab. E.g., for a significance level of 5%, you can use this table. If the red value is greater than the calculated F value, the null hypothesis is rejected, otherwise not. We've seen how ANOVA allows us to compare means across different groups to determine if there are significant differences. But what if our research design involves measurements taken from the same subject at different time points? This is where dependency among the observations comes into play. Let's dive into how repeated measures ANOVA adjusts our approach to interconnected data points. This video is about the repeated measures ANOVA. We will go through the following questions. What is a repeated measures analysis of variance? What are the hypotheses and the assumptions? How is a repeated measures ANOVA calculated? How are the results interpreted? And what is a post hoc test and how do you interpret it? We'll go through all points using a simple example. Let's start with the first question. What is a repeated measures ANOVA? A repeated measures analysis of variance tests whether there is a statistically significant difference between 3 or more dependent samples. What are dependent samples? In a dependent sample, the same participants are measured multiple times under different conditions or at different time points. We therefore have several measurements from each person involved. Let's take a look at an example. Let's say we want to investigate the effectiveness of a training program. For this, we've started looking for volunteers to participate. In order to investigate the effectiveness of the program, we measure the physical fitness of the participants at several points in time, before the training program, immediately after completion, and 2 months later. So for each participant, we have a value for physical fitness before the program, a value immediately after completion, and a value 2 months later. And since we are measuring the same participants at different points in time, we are dealing with dependent samples. Now, of course, it doesn't have to be about people or points in time. In a generalized way, we can say, in a dependent sample, the same test units are measured several times under different conditions. The test units can be people, animals, or cells, for example, and the conditions can be time points or treatments, for example. But what is the purpose of repeated measures ANOVA? We want to know whether the fitness program has an influence on physical fitness. And it is precisely this question that we can answer with the help of an ANOVA with repeated measures. Physical fitness is therefore our dependent variable, and time is our independent variable, with time points as levels. So the analysis of variance with repeated measures checks whether there is a significant difference between the different time points. But isn't that what the paired samples t-test does? Doesn't it also test whether there is a difference between dependent samples? That's correct. The paired samples t-test evaluates whether there is a difference between two dependent groups. The repeated measures ANOVA extends this concept, allowing you to examine differences among 3 or more dependent groups. What are the hypotheses for repeated measures ANOVA? The null hypothesis for a repeated measures ANOVA is that there are no differences between the means of the different conditions or time points. In other words, the null hypothesis assumes that each person has the same value at all times. The values of the individual persons themselves may differ, but one and the same person always has the same value. The alternative hypothesis, on the other hand, is that there is a difference between the dependent groups. In our example, the null hypothesis states that the training program has no influence on physical fitness, i.e. that physical fitness does not change over time, and the alternative hypothesis assumes that the training program does have an influence, i.e. that physical fitness changes over time. To correctly apply repeated measures ANOVA, certain assumptions about the data must be fulfilled. Number 1. Normality. The dependent variable should be approximately normally distributed. This can be tested using the QQ plot or the Kolmogorov-Smirnov test. For more information, please watch my video Tests for Normal Distribution. You can find the link in the video description. Number 2. Sphericity. The variances of the differences between all combinations of factor levels or time points should be the same. This can be tested with the help of Marshall's test for sphericity. If the resulting p-value is greater than 0.05, we can assume that the variances are equal and the assumption is not violated. In this case, the p-value is greater than 0.05. Therefore, this assumption is fulfilled. If the assumption is violated, adjustments such as Greenhouse-Geiser or Hein-Feld can be made. Now I'll show you how to calculate and interpret an analysis of variance online with DataTab. And then we'll go through the formulas to explain how to calculate the analysis of variance with repeated measures by hand. To calculate an ANOVA online, you simply go to datatab.net and copy your own data into this table. I use this example dataset. You can find a link to load this example dataset in the video description. Make sure that your data is structured correctly, i.e. one row per participant and one column per condition or time. Now we click on the Hypothesis Test tab. At the bottom, we see the 3 variables before, in the middle and end from the dataset. If we now click on all of them, a repeated measures ANOVA is automatically calculated. Firstly, we can check the assumptions. Here we see that the Marshall's test for sphericity results in a p-value of 0.357. This value is greater than 0.05 and thus the assumption is fulfilled. If this is not the case, you can tick sphericity correction. I will explain how to test the normal distribution in a separate video. In our example now, we will assume normal distribution with a lot of gnashing of teeth. If the assumption is not fulfilled, you can simply calculate the non-parametric counterpart to the repeated measures ANOVA, the Friedman test. This does not require your data to be normally distributed. First of all, if you do not know exactly how to interpret the individual tables in your analysis, you can simply click on Summary in Words or on AI interpretation for the tables. But now back to the results. First we see the null and the alternative hypothesis. The null hypothesis is that there is no difference between the dependent variables before, in the middle and end. And the alternative hypothesis is that there is a difference. At the end of the test, we can say whether we reject this null hypothesis or not. Now we see the descriptive statistics and a box plot. We then get the results of the ANOVA with repeated measures. In this table, the p-value is the most important value. It is 0.01 and indicates the probability that a sample deviates as much or even more from the null hypothesis as our sample. With a p-value of 0.01, the results are statistically significant at the conventional significance level of 0.05, which means that there are significant differences between the mean values of the three levels before, in the middle and end. This rejects the null hypothesis and we assume that there is a difference between the groups and that the training program or therapy has a significant effect. If you want an interpretation of the other values in this table, simply click on AI interpretation. Finally, here is the table for the Bonferroni post-hoc test. Since the p-value of the analysis of variance is smaller than 0.05, we know that there is a difference between one or more groups. With the post-hoc test, we can now determine between which groups this difference exists. We see that there is a significant difference between before and end, and in the middle and end. Both have a p-value of less than 0.05. How do you calculate an analysis of variance with repeated measures by hand? Let's say this is our data. We have 5 people, each of whom we measured at 3 different points in time. Now we can calculate the necessary mean values. First, we calculate the mean value of all the data, which is 5.4. Then we calculate the mean value of the 3 groups. For the first groups, we get a mean value of 5. For the second, a value of 6.1, and for the third, a value of 5.1. And finally, we can calculate the mean value of the 3 measurements for each person. So for the first person, for example, we have an average value of 8 over the 3 measurements, and for the last person, we have an average value of 5. Now that we have all the mean values, we need to calculate the required sums of squares. But note, our goal is the so-called f-value and subsequently calculate a p-value from it. There are different ways for getting this f-value. I will demonstrate one common way how to do this. Depending on which statistics textbook you use, you may come across a different formula. But back to the calculation. Let's start with the sum of squares within the subjects. We obtain this by calculating each individual value xmi minus the mean value of the respective subject, squaring this and adding it up. So we start with 7 minus 8 squared plus 9 minus 8 squared until finally 3 minus 5 and 7 minus 5. We can then calculate the sum of squares of the treatment, i.e. the sum of squares of the 3 points in time. We obtain this by subtracting the total mean value from each group mean value, squaring it and adding it up. N is the number of people in a group. So we get 5 minus 5.4 squared plus 6.1 minus 5.4 squared plus 5.1 minus 5.4 squared. Now we can calculate the sum of squares of the residual. We get this by simply calculating the sum of squares within the subjects minus the sum of squares of the treatment. Alternatively, we can also use this formula. Here, xmi is again the value of each individual person, ai is the mean value of the respective group, pm is the mean value of the respective person of the 3 points in time, and g is the total mean value. We can then calculate the mean squares. To do this, we divide the respective sum of squares by the degrees of freedom. The mean square of the treatment is therefore calculated by dividing the sum of squares of the treatment by the degrees of freedom of the treatment. The degrees of freedom of the treatment are the number of factor levels minus 1. So we have 3 time points minus 1, which is 2. The mean square of the residual is obtained in the same way. Here the degrees of freedom are the number of factor levels minus 1 times the number of subjects minus 1. We get 2 times 7, which is equal to 14. Now we calculate the F value, which is done by dividing the mean square of the treatment by the mean square of the residual or error. Finally, we calculate the p-value using the F value and the degrees of freedom from the treatment and residual. To calculate the p-value, you can simply go to this page on Data tab. The link can be found in the video description. Here you can enter your values. Our F value is 1.69, the numerator degree of freedom, i.e. that of the treatments, is 2, and the denominator degree of freedom, i.e. that of the error, is 14. We get a p-value of 0.22. The p-value is greater than 0.05, and therefore we do not have enough evidence to reject the null hypothesis. Of course, we can then compare the results with Data tab. To do this, we copy the data back into this table and click on the variables. We can see that we also get a p-value of 0.22 here. After exploring how repeated measures ANOVA can be used to analyze data, we might wonder how to handle even more complex designs. This is where mixed model ANOVA comes in. Let's find out how this powerful tool can help us. What is a mixed model ANOVA? What are the hypotheses and assumptions? And how to interpret the results of a mixed model ANOVA? This is what we discuss in this video. Let's start with the first question. What is a mixed model ANOVA? A mixed model ANOVA is a statistical method used to analyze data that involves both between subject factors and within subject factors. But what are between subject factors and within subject factors? Let's look at an example. Let's say we want to test whether different diets have an effect on cholesterol levels. We would like to compare the 3 diets A, B and C. So the factor diet has the 3 levels A, B and C. To test whether there is a difference between the diets, we are conducting a study with 18 participants. The individual participants are called subjects. Now we randomly assign 6 participants to each of the 3 groups. Each participant or subject is assigned to only one group. In this case, we have a between subjects factor. Different subjects are exposed to different levels of a factor. In this analysis, our objective is to determine whether significant differences exist in the mean cholesterol levels among the various groups under study. And this is exactly what a one-way ANOVA does. Now, of course, we could also examine the impact of one diet across multiple time points. We could measure the cholesterol levels at each participant at the start of the diet, after 2 weeks and after 4 weeks. So the factor time has the 3 levels start, 2 weeks and 4 weeks. And in this case, the same subjects are being exposed to all levels of the factor. And this is called a within subjects factor. The same subjects are exposed to all levels or conditions. In this case, we want to know if there is a difference in the mean value of the cholesterol levels between the different points in time. And this is exactly what a repeated measures ANOVA does. Therefore, in a repeated measures ANOVA, we have within subject factors. So, in a between subjects design, each subject or participant is only assigned to one factor level, so that the different subjects only have the influence of the respective group. In contrast, in a within subjects design, the same subjects or participants are exposed to all factor levels, which enables a direct comparison of the reactions to each factor level. But what if we want to test if there is a difference between diet A, B, and C over the different points in time? So we want to test if there is a difference between the diets and if there is a difference between the different time points. Then we need a mixed model ANOVA because we have both, one between subject factor and one within subject factor. So in a mixed model ANOVA, we have at least one between subjects factor and at least one within subjects factor in the same analysis. Note, a mixed model ANOVA is also called a two-way ANOVA with repeated measures, because there are two factors and one of them results from repeated measures. Therefore, the mixed model ANOVA tests whether there is a difference between more than two samples which are divided at least between two factors. One of the factors is a result of measurement repetition. With the help of a mixed model ANOVA, you can now answer three things. First, whether the within subject factor has an effect on a dependent variable. Second, whether the between subject factor has an effect on a dependent variable. And third, whether there is a so-called interaction effect between the two factors. This gives us a good transition to the hypotheses. The first null hypothesis is the mean values of the different measurement times do not differ. There are no significant differences between the groups of the within subject factor. Then, of course, there is the second. The means of the different groups of the between subject factor do not differ. And the third null hypothesis reflects the interaction effect. One factor has no effect on the effect of the other factor. What are the assumptions of a mixed model ANOVA? Normality. The dependent variable should be approximately normally distributed within each group of the dependent variables. This assumption is especially important when the sample size is small. When a sample size is large, ANOVA is somewhat robust to violations of normality. Homogeneity of variances. The variances in each group should be equal. In mixed model ANOVA, this needs to be true for both the within subjects and between subjects factors. The Levene's test can be used to check this assumption. Homogeneity of covariances, sphericity. This applies to the within subjects factors and assumes that the variance of the differences between all combinations of the different groups are equal. What does that mean? Let's start with the differences between all combinations. To do this, we simply need to calculate the difference of the first group minus the second, the difference of the first group and the third group, and the difference of the second group and the third group. These calculated differences should now have the same variance. This assumption can be tested using Marshall's test of sphericity. When this assumption is violated, adjustments to the degrees of freedom, such as Greenhouse-Geiser or Heinfeld, can be used. Independence of observations. This assumes that the observations are independent of each other. This is a fundamental assumption in ANOVA and is usually assured by the study design. No significant outliers. Outliers can have a disproportionate effect on ANOVA, potentially causing misleading results. It's important to identify and address outliers. Let's calculate an example and I'll show you how to interpret the results. Let's say this is our data that we want to analyze. We want to know whether therapy A, B, and C and 3 different time points have an effect on cholesterol levels. Each row is one person. The therapy is the between subject factor and the time with the levels before the therapy in the middle and at the end of the therapy is the within subject factor. So the first patient on therapy A had a cholesterol level of 165 before therapy, a cholesterol level of 145 in the middle, and a cholesterol level of 140 at the end. Let's first calculate the example online with DataTab and then discuss how to interpret the results. To calculate an ANOVA online, simply go to datatab.net and copy your data into this table. You can also load this example dataset using the link in the video description. Then click on Hypothesis Testing. Under this tab, you will find a lot of hypothesis tests, and depending on which variable you click on, you will get an appropriate hypothesis test suggested. If you copy your data up here, the variables will appear down here. If the correct scale level is not automatically detected, you can simply change it under Variables view. For example, if we click on Before, Middle and End, a repeated measures ANOVA is automatically calculated. But we also want to include the therapy, so we just click on Therapy. Now we get a mixed model ANOVA. We can read the 3 null and the 3 alternative hypotheses here. Then we get the descriptive statistics output. And here we see the results of the analysis of variance and also the post hoc test. We'll look at these again in detail in a moment. But if you don't know exactly how to interpret the results, you can also click on Summary in Words. But now back to the results. Most important in this table are these 3 rows. With these 3 rows, you can check if the 3 null hypotheses we stated before are rejected or not. The first row tests your null hypothesis, whether cholesterol level changes over time, so whether the therapies have an effect on cholesterol level. The second row tests whether there is a difference between the respective therapy forms with respect to cholesterol level. And the last row checks if there is an interaction between the 2 factors. You can read the p-value in each case right at the back here. Let's say we set the significance level at 5%. If our calculated p-value is less than 0.05, then the respective null hypothesis is rejected. And if the calculated p-value is greater than 0.05, then the null hypothesis is not rejected. Thus, we see here that the p-value of before, middle and end is less than 0.05, and therefore the values at before, middle and end are significantly different in terms of cholesterol levels. The p-value in the second row is greater than 0.05, therefore the types of therapy have no significant influence on the cholesterol level. It is important to note that the mean value over the 3 time points is considered here. It could also be that in one therapy the blood pressure increases and in the other therapy the blood pressure decreases, but on average over the time points the blood pressure is the same. If this was the case, however, we would have an interaction between the therapies and the time. We test this with the last hypothesis. In this case, there is no significant interaction between therapy and time. So there is an influence over time, but it does not matter which therapy is used. The therapy has no significant influence. If one of the 2 factors has a significant influence, the following 2 tables show which of the combinations differ significantly. So far, we've explored various types of ANOVA and t-test now. These are also called parametric tests and require certain assumptions about the data, like normality. But what happens if our data doesn't meet these assumptions? This is where non-parametric tests come into play. Let's compare these 2 families of tests to understand their differences. Hi, in this video I explain the difference between parametric and non-parametric hypothesis testing. Why are you interested in this topic? You want to calculate a hypothesis test, but you don't know exactly what the difference is between a parametric and a non-parametric test, and you're wondering when to use which test. If you want to calculate a hypothesis test, you must first check the assumptions for the test. One of the most common assumptions is that your data is normally distributed. In simple terms, if your data is normally distributed, parametric tests are used, such as the t-test, analysis of variance, or Pearson correlation. If your data is not normally distributed, Non-parametric tests are used, such as Mann-Whitney U-Test or Spearman's correlation. What about the other assumptions? Of course, you still need to check whether there are other assumptions for the test. In general, however, non-parametric tests make fewer assumptions than parametric tests. So why use parametric tests at all? Parametric tests are generally more powerful than non-parametric tests. What does that mean? Here is an example. You have formulated your null hypothesis: men and women are paid equally. Whether this null hypothesis is rejected depends on the difference in salary, the dispersion of the data, and the sample size. In a parametric test, a smaller difference in salary or a smaller sample is usually sufficient to reject the null hypothesis. If possible, always use parametric tests. What is the structural difference between parametric and non-parametric tests? Let's take a look at Pearson correlation and Spearman's rank correlation, as well as a t-test for independent samples and the Mann-Whitney U-Test. Let's start with the Pearson and Spearman correlation. The Spearman's rank correlation is the non-parametric counterpart to the Pearson correlation. What is the difference between the two correlation coefficients? Spearman correlation does not use raw data, but the ranks of the data. Let's look at an example. We measure the reaction time of 8 computer players and ask their age. When we calculate a Pearson correlation, we simply take the two variables reaction time and age and calculate the Pearson correlation coefficient. However, we now want to calculate Spearman's rank correlation. So first we assign a rank to each person for reaction time and age. The reaction time is already sorted by size. 12 is the smallest value, so gets rank 1. 15 the second smallest, so gets rank 2, and so on and so forth. We are now doing the same with age. Here we have the smallest value, there the second smallest, here the third smallest, fourth smallest, and so on and so forth. Let's take a look at this in a scatter plot. Here we see the raw data of age and reaction time. But now we would like to use the rankings. So we form ranks from the variables age and reaction time. Through this transformation, we have now distributed our data more evenly. To get Spearman's correlation, we simply calculate Pearson correlation from the ranks. So Spearman correlation is equal to Pearson correlation, only that the ranks are used instead of raw values. What about a t-test for independent samples and the Mann-Whitney U-Test? The t-test for independent samples and the Mann-Whitney U-Test check whether there is a difference between two groups. An example: is there a difference between the reaction time of men and women? The Mann-Whitney U-Test is the non-parametric counterpart to the t-test for independent samples. But there is an important difference between the two tests. The t-test for independent samples tests whether there is a mean difference. For both samples, the mean value is calculated and it is tested whether these mean values differ significantly. The Mann-Whitney U-Test, on the other hand, checks whether there is a rank sum difference. How do we calculate the rank sums? For this purpose, we sort all persons from the smallest to the largest value. This person has the smallest value, so gets rank 1. That person has the second smallest value, so gets rank 2. And this person has the third smallest value, and so on and so forth. Now we have assigned a rank to each person. Then we can simply add up the ranks of the first group and the second group. In the first group we get a rank sum of 42, and in the second group a rank sum of 36. Now we can investigate whether there is a significant difference between these rank sums. If you want to know more about the Mann-Whitney U-Test, check out my related video. So we can summarize: the raw data are used for parametric tests and the ranks of the raw data are used for non-parametric tests. The hypothesis test you use usually depends on how many variables you have and whether it is an independent or dependent sample. In most cases, there is always a non-parametric counterpart to parametric tests. So if you do not meet the assumptions for the parametric test, you can use the non-parametric counterpart. But don't worry, DataTab will do its best to help you choose the right hypothesis test. Of course, you can calculate the most common parametric and non-parametric tests with DataTab online. Simply copy your own data into the table and your variables will appear here below. Now click on the variables you want to calculate a hypothesis test for. For example, if you choose salary and gender, a t-test will be calculated. Here you can check the assumptions. If the assumptions are not met, you can simply click on Non-parametric and a Mann-Whitney U-Test will be calculated. If you click on Salary and Company, an analysis of variance is calculated. Or in the non-parametric case, the Kruskal-Wallis-Test. As we've seen, parametric tests rely heavily on the assumption that data are normally distributed. This leads us to an essential step in data analysis, checking our data for normality. Before applying parametric tests, it is crucial to check this assumption. Otherwise, we would get inaccurate results. Let's now look into different methods and statistical tests to check our data for normal distribution.
In this video, I show you how to test your data for normal distribution. First of all, why do you need normal distribution? Let's say you've collected data and you want to analyze this data with an appropriate hypothesis test. For example, a t-test or an analysis of variance. One of the most common requirements for hypothesis testing is that the data used must be normally distributed. Data are normally distributed if the frequency distribution of the data has this bell curve. Now, of course, the big question is, how do you know if your data is normally distributed or not? Or how can you test that? There are two ways. Either you can check the normal distribution analytically or graphically. We now look at both in detail. Let's start with the analytical test for normal distribution. In order to test your data analytically for normal distribution, there are several test procedures. The best known are the Kolmogorov-Smirnov test, the Shapiro-Wilk test, and the Anderson-Darling test. With all these tests, you test the null hypothesis that the data are normally distributed. So, the null hypothesis is that the frequency distribution of your data fits the normal distribution. In order to reject or not reject the null hypothesis, you get a p-value out of all these tests. Now the big question is whether this p-value is greater or less than 0.05. If the p-value is less than 0.05, this is interpreted as a significant deviation from the normal distribution, and you can assume that your data are not normally distributed. If the p-value is greater than 0.05 and you want to be statistically clean, you cannot necessarily say that the frequency distribution corresponds to the normal distribution. You just cannot disprove the null hypothesis. In practice, however, values greater than 0.05 are assumed to be normally distributed. To be on the safe side, you should always take a look at the graphical solution, which we will talk about in a moment. So, in summary, all these tests give you a p-value. If this p-value is less than 0.05, you assume no normal distribution. If it is greater than 0.05, you assume normal distribution. For your information, with the Kolmogorov-Smirnov test and with the Anderson-Darling test, you can also test distributions other than the normal distribution. Now, unfortunately, there is a big disadvantage of the analytical methods, which is why more and more people are switching to using the graphical methods. The problem is that the calculated p-value is influenced by the size of the sample. Therefore, if you have a very small sample, your p-value may be much larger than 0.05, but if you have a very large sample, your p-value may be smaller than 0.05. Let's assume the distribution in your population deviates very slightly from the normal distribution. Then, if you take a very small sample, you will get a very large p-value and thus you will assume that it is normally distributed data. However, if you take a larger sample, then the p-value becomes smaller and smaller, even though the samples come from the same population with the same distribution. Therefore, if you have a minimal deviation from the normal distribution, which isn't actually relevant, the larger your sample, the smaller the p-value becomes. With a very large sample, you may even get a p-value smaller than 0.05 and thus reject the null hypothesis that it is a normal distribution. To get around this problem, graphical methods are being used more and more. We'll come to that now. If the normal distribution is checked graphically, you either look at the histogram or even better at the QQ plot. If you use the histogram, you plot the normal distribution in the histogram of your data, and then you can see whether the curve of the normal distribution roughly corresponds to that of the normal distribution curve. However, it is better if you use the so-called quantile-quantile plot or QQ plot for short. Here, the theoretical quantiles that the data should have if they are perfectly normally distributed and the quantiles of the measured values are compared. If the data is perfectly normally distributed, all points would lie on the line. The more the data deviates from the line, the less it is normally distributed. In addition, DataDep plots the 95% confidence interval. If all or almost all of your data lies within this interval, it is a very strong indication that your data is normally distributed. Your data would not be normally distributed if, for example, they form an arc and lie far away from the line in some areas. If you use DataDep in order to test for normal distribution, you get the following evaluation. First, you get the analytical test procedures clearly arranged in a table. Then come the graphical test procedures. How you can test your data with DataDep for normal distribution, I will show you now. Just copy your data into this table. Click on Descriptive Statistics and then select the variable you want to test for normal distribution. For example, age. After that, you can simply click on Test for normal distribution here, and you will get the results down here. I know the test procedures are not actually descriptive methods, but if you want to get an overview of your data, it's usually also relevant to look at the distribution of your data. Furthermore, if you calculate a hypothesis test, for example whether gender has an influence on the salary of a person, then you can check the preconditions for each hypothesis test, and you will also get the test for normal distribution. If the precondition is not met, you would click on this, and a non-parametric test, the Mann-Whitney U-Test, would be calculated. The Mann-Whitney U-Test does not need normally distributed data.
Another important assumption is the equality of variance. You can check whether two or more groups have the same variance using the Levene's test. Let's take a look at it. What is a Levene's test? Levene's test tests the hypothesis that the variances are equal in different groups. The aim is to determine whether the variances in different groups are significantly different from each other. The hypotheses for Levene's test are as follows. The null hypothesis is the variances of the groups are equal. And the alternative hypothesis is at least one of the groups has a different variance. When is Levene's test most commonly used? Levene's test is most often used to test assumptions for another hypothesis test. What does that mean? Let's say your hypothesis is there is a difference between two medications in terms of perceived pain relief. To test this hypothesis, you've collected data. Now, to test the hypothesis based on your data, you use a hypothesis test such as a t-test. Many hypothesis tests have the assumption that the variances in each group are equal, and this is where Levene's test comes in. It tells us whether this assumption is fulfilled or not. How is a Levene's test calculated? Here's an example. We want to know if there is a significant difference in variance between these groups. First, we simply calculate the mean of each group. Then, we subtract the respective group mean from each person. The amount of each value is now formed so that the negative values become positive. From these new values, the group mean can now be calculated again. The larger the group mean, the greater the variance within each group. Thus, there is a smaller variance in this group than in that group. In addition, we can calculate the total mean value. Now we can calculate the squared deviations of the group means from the overall mean and sum them up. And then we can calculate the squared deviation of the individual values from the respective group mean and add them up. We can now compare the two calculated sums. And that is exactly what Levene's test does. The test statistic of Levene's test is obtained with this equation. N is the number of cases, Ni the number of cases in the ith group, Zi is the mean value of the ith group, Z is the overall average, Zij is the respective value in the groups, and K is the number of groups. The calculated test statistic L is equal to the F statistic. Therefore, with the F value and the degrees of freedom, the P value can be calculated. The degrees of freedom result with number of groups minus 1 and number of cases minus number of groups. If the P value is greater than 0.05, the null hypothesis that the variances are equal is not rejected. Thus, equality of variance can be assumed. If you use Data tab and calculate an analysis of variance, you can find Levene's test under Test Assumptions. In an independent t-test, you will find Levene's test at the bottom of the results. If equality of variance is not given, you can use the t-test for unequal variance. Now that we understand the importance of testing for normal distribution, we might find ourselves in a situation where our data do not meet these assumptions. In this case, we turn to non-parametric methods that are less sensitive to the distribution of data. We will discuss various kinds of tests for this purpose, like Mann-Whitney U-Test, Kruskal-Wallis-Test, Wilcoxon signed rank test, and Friedman Test. Let's start with the non-parametric counterpart to the t-test for independent samples, the Mann-Whitney U-Test. What is a Mann-Whitney U-Test and how is it calculated? That's what we will discuss in this video. Let's start with the first question. What is a Mann-Whitney U-Test? A Mann-Whitney U-Test tests whether there is a difference between two independent samples. An example. Is there a difference between the reaction time of women and men? But the t-test for independent samples does the same. It also tests whether there is a difference between two independent samples. That's right. The Mann-Whitney U-Test is the non-parametric counterpart to the t-test for independent samples. But there is an important difference between the two tests. The t-test for independent samples tests whether there is a mean difference. For both samples, the mean value is calculated and it is tested whether these mean values differ significantly. The Mann-Whitney U-Test, on the other hand, checks whether there is a rank sum difference. How do we calculate the rank sum? For this purpose, we sort all persons from the smallest to the largest value. This person has the smallest value, so gets rank 1. This person has the second smallest value, so gets rank 2. And this person has the third smallest value, and so on and so forth. Now we have assigned a rank to each person. Then we can simply add up the ranks of the first group and the second group. In the first group we get a rank of 42 and in the second group a rank of 36. Now we can investigate whether there is a significant difference between these rank sums, but more on that later. The advantage of taking the rank sums rather than the difference in means is that the data need not to be normally distributed. So in contrast to the t-test, the data in the Mann-Whitney U-Test do not have to be normally distributed. What are the hypotheses of the Mann-Whitney U-Test? The null hypothesis is, in the two samples, the rank sums do not differ significantly. The alternative hypothesis is, in the two samples, the rank sums do differ significantly. Now let's go through everything with an example. First we calculate the example with datatab, and then we see if we can get the same results by hand. If you like, you can load the sample dataset to follow the example. You can find a link in the video description. We simply click on datatab.net and open the statistics calculator. I've already loaded the data from the link here. You can also copy your own data into this table. Then all you have to do is click on the Hypothesis Test tab and then simply select the desired variables. We measure the reaction time of a group of men and women and want to know if there is a difference in reaction time. So we click on Response Time and Gender. We don't want to calculate a t-test for independent samples, but a Mann-Whitney U-Test. So let's just click on Non-parametric Test. Here we see the results of the Mann-Whitney U-Test. If you're not sure how to interpret the results, just click on Summary in Words. For the given data, a Mann-Whitney U-Test showed that the difference between female and male with respect to the dependent variable response time was not statistically significant. Thus, the null hypothesis is not rejected. So we now calculate the Mann-Whitney U-Test by hand. For this, we have plotted the values in a table. On one side, we have gender with female and male, and on the other side, the values for reaction time. Unfortunately, the data is not normally distributed, so we cannot use a t-test, and we calculate the Mann-Whitney U-Test instead. First, we assign a rank to each value. We pick the smallest value, which is 33, which gets the rank 1. The second smallest value is 34, which gets the rank 2. The third smallest value is 35, which gets the rank 3. Now we do the same for all other values. So now we have all ranks assigned and we can just add up all the ranks from women and all the ranks from men. The rank sum is abbreviated with T and we get T1 for female with 2 plus 4 plus 7 plus 9 plus 10 plus 5, which is 37. Now we do the same for male. Here we get 11 plus 1 plus 3 plus 6 plus 8, which is 29. Again, our null hypothesis is that both rank sums are equal. Now we want to calculate the p-value for this. We have once calculated the rank sum for the female participants and we have the number of cases of 6. Therefore, we have 6 female subjects. We can now calculate the U1.
that is the U for the female participants using this formula. Here we have N1 and N2, that is the number of cases of female and male, minus the rank sum of the female participants. If we insert our values, we get a U1 of 14. We now do exactly the same for the male participants and we get a U2 of 16. So now we have calculated U1 and U2. The U for the Mann-Whitney U-Test is now given by the smaller value of the two. So in our case, we take the minimum of 14 and 16. This is of course 14. Next, we need to calculate the expected value of U, which we get by N1 times N2 divided by 2. In our case, it is 6 times 5 divided by 2, and that is equal to 15. Last but not least, we need the standard error of U. The standard error can be calculated with this formula, and in our case, it is equal to 5.4772. With all these values, we can now calculate Z. The Z value results with U minus mu U divided by the standard error. In our case, we get 14 minus 15 divided by 5.4772, which is equal to minus 0.1825. So now we have the Z value, and with the Z value, we can calculate the p-value. However, it should be noted, depending on how large the sample is, the p-value for the Mann-Whitney U-Test is calculated in different ways. For up to 25 cases, the exact values are used, which can be read from a table. For large samples, the normal distribution of the U value can be used as an approximation. In our example, we would actually use the exact values, nevertheless we assume a normal distribution. For this, we can simply go to Data tab and calculate the p-value for a given Z value. The p-value of 0.855 is significantly greater than the significance level of 0.05, and thus the null hypothesis cannot be rejected based on this sample. How to calculate the Mann-Whitney U-Test on tied ranks you can learn in our tutorial on datatab.net. You find the link in the video description.
But what if we want to compare two dependent samples and need a non-parametric test? Let's take a look at Wilcoxon signed rank test.
In this video, I will explain the Wilcoxon test to you. We will go through what Wilcoxon test is, what the assumptions are, and how it is calculated. And at the end, I will show you how you can easily calculate the Wilcoxon test online with DataTab. And we get started right now. The Wilcoxon test analyzes whether there's a difference between two dependent samples or not. Therefore, if you have two dependent groups, you want to test whether there is a difference between these two groups, then you can use the Wilcoxon test. Now you rightly say, hey, the t-test for dependent samples does the same thing. It also tests whether there's a difference between two dependent groups. That's correct, of course. The Wilcoxon test is the non-parametric counterpart of the t-test for dependent samples. The special thing about Wilcoxon test is that your data do not have to be normally distributed. To put it simple, if your data are normally distributed, you use a parametric test. In the case of two dependent samples, this is the t-test for dependent samples. If your data is not normally distributed, you use a non-parametric test. In the case of two dependent samples, this would be the Wilcoxon test. Now, of course, you could say, well, then I'll just always use the Wilcoxon test and I don't even have to check the normal distribution. At the end of this video, I will show you why you should always use the t-test if it's possible to do so. First, I have a little reminder for you what dependent samples are. In dependent samples, the measured values are always available in pairs. The pairs result from, for example, repeated measures of the same person. But what is the difference now between the t-test for dependent samples and the Wilcoxon test? The t-test for dependent samples tests whether there's a difference in means. If we have a dependent sample, say we took a value from each person once in the morning and once in the evening, then we can calculate the difference from each pair. So for example, we would have 45 minus 34, which equals 11. The t-test for dependent sample now tests whether these differences differ from 0 or not. In the Wilcoxon test, we don't use the differences of means, but we form ranks and then we compare these ranks with each other. 3 is the smallest value in terms of amount. It gets rank 1. 4 is the second smallest value and it gets rank 2. 6 gets rank 3 and 11 gets rank 4. We assign a plus to all positive values and a minus to all negative values. But don't worry, we will go through this slowly and we'll also look at an example. Now we go to the assumptions and the hypotheses. In the Wilcoxon test, only 2 dependent random samples with at least ordinally scaled characteristics need to be present. The variables do not have to satisfy a distribution curve. What should be mentioned now, however, is that the distribution shape of the differences of the 2 dependent samples should be approximately symmetric. The null hypothesis in the Wilcoxon test is that there is no difference in the so-called central tendency of the 2 samples in the population. That is, that there is no difference between the dependent groups. The alternative hypothesis is that there is a difference in the central tendency in the population, so we expect that the 2 dependent groups are different. So now we finally look at a quite simple example. Let's say you have measured the reaction time of a small group of people once in the morning and once in the evening, and you want to know if there is a difference between morning and evening. In order to do this, you measure the reaction time of 7 people in the morning and in the evening. The measured values are therefore available now in pairs. And now you want to calculate the difference between morning and evening. If the difference would be normally distributed, you would use a t-test for dependent samples. If it is not, we would use a Wilcoxon test. Let's just assume that there is no normal distribution and we need to calculate a Wilcoxon test. In order to do this, the first thing we do is we form ranks. We look for the smallest value in terms of amount, that is -2, which gets rank 1. What is the second smallest value? That is 3, which gets rank 2, and so on and so forth, until we have ranked all the values. The next thing is that we look at the differences and we try to figure out which difference is positive and which is a negative one. For the negative differences, we simply add a minus. Then we can add up the positive ranks and the negative ranks. For the positive ranks, we get 7 plus 2 plus 3 plus 4 plus 6, which is equal to 22. For the negative ranks, we get 5 plus 1, which is equal to 6. If there is no difference between morning and evening, the positive and negative ranks should be approximately equal. Therefore, the null hypothesis is that both rank sums are equal. But how can we test this? Now we have the sum of ranks and we use it to calculate the test statistic W. This is simply the minimum value of t plus and t minus. In our case, it is the minimum value of 22 and 6, and therefore the test statistic W in our case is 6. Now we can further calculate the value for t or w that we would expect if there was no difference between morning and evening. In this case, we would get a value of 14. Therefore, if there is no difference between morning and evening, we would actually expect a value for t plus and t minus of 14. And thus, w would also be 14. Further, we can calculate the standard deviation. This is given by this, to be fair, a little bit complicated formula. Once we are finished with that, we can now calculate the z value. The z value is obtained by calculating w minus mu and dividing that by the standard deviation. So we compare the value that would be expected if there was no difference with the value that actually occurred. Note that if there are more than 25 cases, normal distribution is assumed, in which case we can calculate the z value using this formula. If there are less than 25 values, the critical t-value is read from a table of critical t-values. Therefore, in our case, we would actually use the table. Now I will show you how you can easily calculate the Wilcoxon test online. And then I will go into why you should always prefer the dependent t-test to the Wilcoxon test if it's possible. In order to calculate the Wilcoxon test, simply go to datadep.net. You will also find the link in the video description, and you copy your own data into this table. Then you click on this tab and you will see the names of all your variables that you copied into the table above. Underneath this tab, many hypothesis tests are summarized, and DataTab automatically suggests the appropriate hypothesis test for your data. If you now select morning and evening, DataTab automatically recognizes that it is a dependent sample and calculates the dependent t-test. But we don't want to calculate a t-test, we want to calculate the Wilcoxon test. So we just click here. Now DataTab automatically calculates the Wilcoxon test. Here we can read the negative and positive ranks, and here we see the z value and the p-value. If you don't know exactly how this is interpreted, just look at the summary in words. It says that the morning group had lower values than the evening group, and a Wilcoxon test showed that this difference was not statistically significant. P equals 0.312.
And finally, we can take a look at the non-parametric counterpart of the ANOVA. Let's start with the Kruskal-Wallis-Test.
This tutorial is about the Kruskal-Wallis-Test. The Kruskal-Wallis-Test is a hypothesis test that is used when you want to test whether there is a difference between several independent groups. Now you may wonder a little bit and say, hey, if there are several independent groups, I use an analysis of variance. That's right, but if your data are not normally distributed and the assumptions for the analysis of variance are not met, the Kruskal-Wallis-Test is used. The Kruskal-Wallis-Test is the non-parametric counterpart of the single-factor analysis of variance. I will now show you what that means. There is an important difference between the two tests. The analysis of variance tests if there is a difference in means. So when we have our groups, we calculate the mean of the groups and check if all the means are equal. When we look at the Kruskal-Wallis-Test, on the other hand, we don't check if the means are equal, we check if the rank sums of all the groups are equal. What does that mean now? What is a rank and what is a rank sum? In the Kruskal-Wallis-Test, we do not use the actual measured values, but we sort all people by size, and then the person with the smallest value gets the new value or rank 1. The person with the second smallest value gets rank 2. The person with the third smallest value gets rank 3, and so on and so forth, until each person has been assigned a rank. Now we have assigned a rank to each person, and then we can simply add up the ranks from the first group, add up the ranks from the second group, and add up the ranks from the third group. In this case, we get a rank sum of 42 for the first group, 70 for the second group, and 47 for the third group. The big advantage is that if we do not look at the mean difference, but at the rank sum, the data does not have to be normally distributed. When using the Kruskal-Wallis-Test, our data does not have to satisfy any distributional form, and therefore we also don't need it to be normally distributed. Before we discuss how the Kruskal-Wallis-Test is calculated, and don't worry, it's really not complicated, we first take a look at the assumptions. When do we use the Kruskal-Wallis-Test? We use the Kruskal-Wallis-Test if we have a nominal or ordinal variable with more than two values and a metric variable. A nominal or ordinal variable with more than two values is, for example, the variable preferred newspaper with the values Washington Post, New York Times, USA Today. It could also be frequency of television viewing with daily, several times a week, rarely, never. A metric variable is, for example, salary, well-being, or weight of people. What are the assumptions now? Only several independent random samples with at least ordinally scaled characteristics must be available. The variables do not have to satisfy a distribution curve. So the null hypothesis is the independent samples all have the same central tendency and therefore come from the same population. Or in other words, there's no difference in the rank sums. And the alternative hypothesis could be at least one of the independent samples does not have the same central tendency as the other samples and therefore comes from a different population. Or to say it in other words again, at least one group differs in rank sums. So the next question is, how do we calculate a Kruskal-Wallis test? It's not difficult. Let's say you have measured the reaction time of three groups, Group A, Group B, and Group C. And now you want to know if there's a difference between the groups in terms of reaction time. Let's say you've written down the measured reaction time in a table. Let's just assume that the data is not normally distributed and therefore you have to use the Kruskal-Wallis test. So then our null hypothesis is that there is no difference between the groups. And we're going to test that right now. First, we assign a rank to each person. This is the smallest value, so this person gets rank 1. This is the second smallest value, so this person gets rank 2. And we do this now for all people. If the groups have no influence on reaction time, the ranks should actually be distributed purely randomly. In a second step, we now calculate the rank sum and the mean rank sum. For the first group, the rank sum is 2 plus 4 plus 7 plus 9, which is equal to 22. And we have 4 people in the group, so the mean rank sum is 22 divided by 4, which equals 5.5. Now we do the same for the second group. Here we get a rank sum of 27 and the mean rank sum of 6.75. And for the third group we get a rank sum of 29 and a mean rank sum of 7.25. Now we can calculate the expected value of the rank sums. The expected value, if there is no difference in the groups, would be that each group would have a rank sum of 6.5. We've now almost got everything we need. We interviewed 12 people, so the number of cases is 12. The expected value of the ranks is 6.5. We've also calculated the mean rank sums of the individual groups. The degrees of freedom in our case are 2, and these are simply given by the number of groups minus 1, which makes 3 minus 1. Last, we need the variance. The variance of ranks is given by n to the power of 2 minus 1 divided by 12. N is again the number of people, so 12, so we get a variance of 11.92. Now we've got everything we need. With these values, we can now calculate our test value H. The test statistic H corresponds to the chi-square value and is given by this formula. N is the number of cases, R bar is the mean rank sum of the individual groups, and ER is the expected value of the ranks. Sigma squared is the variance of the ranks. In our case, the number of cases is 12. We always have 4 people per group, so we can pull out the NE. 5.5 is the mean rank of group A, 6.75 is the mean rank of group B, and 7.25 is the mean rank of group C. This gives us a rounded H value of 0.5. As we just said, this value corresponds to the chi-square value, so now we can easily read the critical chi-square value in the table of critical chi-square values. You find this table on datatab.net. We have 2 degrees of freedom, and if we assume that we have a significance level of 0.05, we get a critical chi-squared value of 5.991. So of course our value is smaller than the critical chi-squared value, and so based on our example data, the null hypothesis is retained. And now I will show you how we can easily calculate the Kruskal-Wallis-Test online with Datatab. In order to do this, you simply visit datatab.net. You will find a link in the video description, and then you click on the Statistics Calculator and insert your own data into this table. Further, you click on this tab, and under this tab you will find many hypothesis tests, and when you select the variables you want to test, Datatab will suggest the appropriate test. After you've copied your data into the table, you will see the reaction time and group right here at the bottom. Now we simply click on reaction time and group, and Datatab automatically calculates an analysis of variance for us. But we don't want an analysis of variance. We want the non-parametric test, so we just click here. Now Datatab automatically calculates the Kruskal-Wallis-Test. We also get a chi-square value of 0.5, the degrees of freedom are 2, and the calculated p-value is 0.779. And here below you can read the interpretation in words. A Kruskal-Wallis-Test showed that there is no significant difference between the categories. P makes 0.779. Therefore, with the data used, the null hypothesis is not rejected. If we have 3 or more dependent samples, we can use the Friedman test as a non-parametric alternative to the ANOVA with repeated measures. This video is about the Friedman test, and we start right away with the first question: what is the Friedman test? The Friedman test analyzes whether there are statistically significant differences between 3 or more dependent samples. What is a dependent sample again? In a dependent sample, the measured values are linked. For example, if a sample is drawn of people who have knee surgery, and these people are interviewed before the surgery and 1 and 2 weeks after the surgery, it is a dependent sample. This is the case because the same person was interviewed at multiple time points. Now you might rightly say that the analysis of variance with repeated measures tests exactly the same thing, since it also tests whether there is a difference between 3 or more dependent samples. That is correct. The Friedman test is the non-parametric counterpart of the analysis of variance with repeated measures. But what is the difference between the 2 tests? The analysis of variance tests the extent to which the measured values of the dependent sample differ. In the Friedman test, on the other hand, it is not the actual measured values that are used, but the ranks. The time where a person has the highest value gets rank 1, the time with the second highest value gets rank 2, and the time with the smallest value gets rank 3. This is now done for all people or for all rows. Afterwards, the ranks of the single points of time are added up. At the first time point, we get a sum of 7. At the second time point, we get a sum of 8. And at the third time point, we get a sum of 9. Now we can check how much these rank sums differ from each other. But why are rank sums used? The big advantage is that if you don't look at the mean differences but at the rank sum, the data doesn't have to be normally distributed. To put it simple, if your data are normally distributed, parametric tests are used. For more than 2 dependent samples, this is the analysis of variance with repeated measures. If your data are not normally distributed, non-parametric tests are used. For more than 2 dependent samples, this is the Friedman test. This leads us to the research question that you can answer with the Friedman test. Is there a significant difference between more than 2 dependent groups? Let's have a look at that with an example. You might be interested to know whether therapy after a slipped disc has an influence on the patient's perception of pain. For this purpose, you measure the pain perception before the therapy, in the middle of the therapy, and at the end of the therapy. Now you want to know if there is a difference between the different times. So your independent variable is time or therapy progressing over time. Your dependent variable is the pain perception. You now have a history of the pain perception of each person over time. And now you want to know whether the therapy has an influence on the pain perception. Simplified, in this case, the therapy has an influence, and in that case, the therapy has no influence on the pain perception. In the course of time, the pain perception does not change here. In this case, it does. Now we also have a good transition to the hypotheses. In the Friedman test, the null hypothesis is there are no significant differences between the dependent groups. And the alternative hypothesis is there is a significant difference between the dependent groups. Of course, as already mentioned, the Friedman test does not use the true values, but the ranks. We will go through the formula behind the Friedman test in a moment. This brings us to the point of how to calculate the Friedman test. For the calculation of the Friedman test, you can of course simply use data tab or calculate it by hand. To be honest, hardly anyone will calculate the Friedman test by hand, but it will help you to understand how the Friedman test works, and don't worry, it's not that complicated. First, I will show you how to calculate the Friedman test with data tab, and then I will show you how to do it by hand. In order to do this, simply go to datatab.net and copy your own data into this table. Let's say you want to investigate whether there is a difference in the response time of people in the morning, at noon, and in the evening. We simply click on this tab. Under this tab, you will find many hypothesis tests, and data tab will automatically suggest an appropriate test. If we click on all 3 variables, morning, noon, and evening, data tab will automatically calculate an analysis of variance with repeated measures. But in our case, we want to calculate the non-parametric test, so we click here. Now we get the results for the Friedman test. Up here, you can read the descriptive statistics, and down here, you can find the p-value. If you don't know exactly how to interpret the p-value, you can just read the interpretation in words down here. A Friedman test showed that there is no significant difference between the variables chi² equals 2.57, p equals 0.276. If your p-value is greater than your set significance level, then your null hypothesis is retained. The null hypothesis is that there is no difference between the groups. Usually a significance level of 0.05 is used, so this p-value is greater than 0.05. Additionally, DataTab gives you the post hoc test. If your p-value is smaller than 0.05, the post hoc test helps you to examine which of the groups really differ. So now let's look at what the equation behind the Friedman test are and recalculate this example by hand. Here we have the measured values of the 7 people. In the first step, we have to assign ranks to the values. In order to do this, we look at each row separately. In the first row, which is the first person, 45 is the largest value. This gets rank 1. Then comes 36 with rank 2 and 34 with rank 3. We do the same for the second row. Here, 36 is the largest value and gets rank 1. Then comes 33 with rank 2 and 31 with rank 3. Now we do this for each row, so for all people. Afterwards, we can calculate the rank sum for each point in time. For example, we just sum up all ranks at one point in time. In the morning, we get 17, at noon 11, and in the evening 14. If there were no differences between the different time points in terms of reaction time, we would expect the expected value at all time points. The expected value is obtained with this formula, and in this case it is 14. So if there is no difference between morning, noon and evening, we would actually expect a rank sum of 14 at all 3 time points. Next, we can calculate the chi-square value. We get it with this formula. N is the number of people, which is 7. K is the number of time points, so 3, and the sum of r squared is 17 squared plus 11 squared plus 14 squared. So we get a chi-square value of 2.57. Now we need the number of degrees of freedom. This is given by the number of time points minus 1, so in our case 2. Finally, we can read the critical chi-square value in the table of critical chi-square values. For this, we take the predefined significance level, let's say it is 0.05, and the number of degrees of freedom. Here we can read that the critical chi-square value is 5.99. This is greater than our calculated value. Therefore, the null hypothesis is not rejected, and based on these data, there is no difference between the responsiveness at the different time points. Therefore, the null hypothesis is not rejected, and based on these data, there is no difference between the responsiveness at the different time points. If the calculated chi-square value was greater than the critical one, we would reject the null hypothesis.
Having explored various non-parametric tests for ordinal or non-normally distributed metric data, now let's shift our focus to nominal data. When our variables are nominal, such as gender or color preferences, we require a different kind of statistical test, the chi-square test. The chi-square test is a powerful tool for analyzing nominal data. Let's get started. What is a chi-square test and how is the chi-square test calculated? That's what we will discuss in this video. Let's start with the first question. What is a chi-square test? The chi-square test is a hypothesis test that is used when you want to determine if there is a relationship between two categorical variables. What are categorical variables again? Categorical variables are, for example, gender with the categories male and female, the preferred newspaper with the categories USA Today, the Wall Street Journal, the New York Times, and so on, or the highest educational level with the categories
without graduation, college, bachelor's degree, master's degree. So gender, preferred newspaper, and highest educational level are all categorical variables. For example, no categorical variables are the weight of a person, the salary of a person, or the power consumption. If we now have two categorical variables and we want to test whether there is a relationship, we use a chi-square test. For example, is there a relationship between gender and the preferred newspaper? We have two categorical variables, so we use a chi-square test. Another example, is there a relationship between preferred newspaper and highest educational level? Here again we have two categorical variables, so we use a chi-square test. However, there are two things to note. First, the assumption for the chi-square test is that the expected frequencies per cell are greater than 5. We'll go over what that means in a moment. Second, the chi-square test uses only the categories and not the rankings. However, in the case of the highest educational level, there's a ranking of categories. If you want to account for rankings, check out our tutorials on Spearman correlation, Mann-Whitney U-Test or Kruskal-Wallis-Test. But how do we calculate the chi-square test? Let's go through that with an example. We would like to investigate whether gender has an influence on the preferred newspaper. So our question is there a relationship between gender and the preferred newspaper? Our null hypothesis is there is no relationship between gender and the preferred newspaper. And our alternative hypothesis is there is a relationship between gender and the preferred newspaper. So first we create a questionnaire that asks about gender and the preferred newspaper. We will then send out the questionnaire. The results of the survey are displayed in a table. In this table, we see one respondent in each row. The first respondent is male and stated New York Post. The second respondent is female and stated USA Today. We can now copy this table into a statistics software like DataDab. DataDab then gives us the so-called contingency table. In this table, you can see the variable newspaper and the variable gender. The number of times each combination occurs is plotted in the cells. For example, in this survey, there are 16 people who stated New York Post and male, or 13 people who stated female and New York Post. Now we want to know if gender has an influence on the preferred newspaper. Or put another way, is there a relationship between gender and the preferred newspaper? Now, to answer this question, we use the chi-square test. There are two ways we can calculate the chi-square test. Either we use a statistical software like DataDab, or we calculate the chi-square test by hand. We start with the uncomplicated variant and use DataDab. If you like, you can load the sample dataset for calculation. You can find the link in the video description. To calculate a chi-square test online, simply copy your own data into this table or use the link to load this dataset. Then the variables gender and newspaper appear here below. Now we click on Hypothesis Test. Here you will find a variety of tests and DataDab will help you to choose the right one. For example, if we click on Gender and Newspaper, the chi-square test will be automatically calculated. Now we get the results for the chi-square test. Above we see the contingency table for the variables gender and newspaper. The contingency table shows us how often the respective combinations occur in our survey. Female and USA Today, for example, occurs 6 times. In the second table, we can see what the contingency table should actually look like if the two variables were perfectly independent. That is, if gender had no influence on the preferred newspaper. Here it is important to note that all of the frequencies should be larger than 5 so that the assumptions of the chi-square test are fulfilled. But this is the case here. The chi-square test now compares this table with that table. And here we see the results. The p-value is 0.91, which is much higher than our significance level of 0.05, and therefore we keep the null hypothesis. If you don't know exactly how to interpret the results, just click on Summary in Words. A chi-square test was performed between gender and newspaper. All expected cell frequencies were greater than 5, thus the assumptions for the chi-square test were met. There was no statistically significant relationship between gender and newspaper. This results in a p-value of 0.918, which is above the defined significance level of 5%. The chi-square test is therefore not significant and the null hypothesis is not rejected. If you're unsure what exactly the p-value means, just watch our video about the p-value. And now we come to the question how to calculate the chi-square test by hand, and we go through the formulas needed. Don't worry, it's not difficult. We need the contingency table with the observed frequencies, the contingency table with the expected frequencies. That is, those frequencies that would occur with perfectly independent variables. You can find how to calculate the expected frequencies on Data tab in the tutorial on the chi-square test. We can now calculate the chi-square with this formula. The index k stands for the respective cell, OK is the observed frequency, EK is the expected frequency. So we get 6 minus 6.08 squared divided by 6.08 plus the next cell, 7 minus 6.92 squared divided by 6.92. If we do this for all cells and sum them up, we get a chi-square of 0.504. So this results in a chi-square value of 0.504. Now we would like to calculate the critical chi-square value. What do we need it for? If we use a statistical software, we simply get a p-value displayed. If the value is smaller than the significance level, for example 0.05, the null hypothesis is rejected, otherwise not. In our example case, the null hypothesis is not rejected. By hand, however, you can't really calculate the p-value. Therefore, you read off in a table which chi-square value you would get with a p-value of 0.05. This chi-square value is called the critical chi-square value. In order to calculate the critical chi-square value, we need the degrees of freedom. These are obtained by taking the number of rows minus 1 times the number of columns minus 1. We have 4 rows and 2 columns. Therefore, we get 3 times 1 and thus 3 degrees of freedom. Now let's take a look at the table of critical chi-square values. You can find this table on Data tab. The link is in the video description. We select a significance level of 0.05 and have 3 degrees of freedom. Therefore, our critical chi-square value is 7.815. The critical chi-square value of 7.815 is larger than our calculated chi-square value of 0.504. Thus, the null hypothesis is retained.
Up until now, we focused on statistical tests designed to compare groups or categories. Another fundamental aspect of data analysis is understanding the relationship between variables. This is where correlation comes into play. Let's transition from tests of differences to measures of association in the following video.
This video is about correlation analysis. We start by asking what a correlation analysis is. We will then look at the most important correlation analysis,
Pearson correlation, Spearman correlation, Candle's tau and point biserial correlation. And finally, we will discuss the difference between correlation and causation. Let's start with the first question. What is a correlation analysis? Correlation analysis is a statistical method used to measure the relationship between two variables. For example, is there a relationship between a person's salary and age? In this scatter plot, every single point is a person. In correlation analysis, we usually want to know two things. Number one, how strong the correlation is, and number two, in which direction the correlation goes. We can read both in the correlation coefficient, which is between -1 and 1. The strength of the correlation can be read in a table. If R is between 0 and 0.1, we speak of no correlation. If R is between 0.7 and 1, we speak of a very strong correlation. A positive correlation exists when high values of one variable go along with high values of the other variable, or when small values of one variable go along with small values of the other variable. A positive correlation is found, for example, for body size and shoe size. The result is a positive correlation coefficient. A negative correlation exists when high values of one variable go along with low values of the other variable, and vice versa. A negative correlation usually exists between product price and sales volume. The result is a negative correlation coefficient. Now we have different correlation coefficients. The most popular are Pearson correlation coefficient R, Spearman correlation coefficient RS, Candle's tau, and point biserial correlation coefficient RPB. Let's start with the first, the Pearson correlation coefficient. What is a Pearson correlation? As all correlation coefficients, the Pearson correlation R is a statistical measure that quantifies the relationship between two variables. In the case of Pearson correlation, the linear relationship of metric variables is measured. More about metric variables later. So with the help of Pearson correlation, we can measure the linear relationship between two variables. And of course, the Pearson correlation coefficient R tells us how strong the correlation is and in which direction the correlation goes. How is Pearson correlation calculated? The Pearson correlation coefficient is obtained via this equation, where R is the Pearson correlation coefficient, xi are the individual values of one variable, for example age, yi are the individual values of the other variable, for example salary, x dash and y dash are respectively the mean values of the two variables. In the equation, we can see that the respective mean value is first subtracted from both values. So in our example, we calculate the mean values of age and salary. We then subtract the mean values from each person's age and salary. Then we multiply both values and we sum up the individual results of the multiplication. The expression in the denominator ensures that the correlation coefficient is scaled between -1 and 1. If we now multiply two positive values, we get a positive value. So all values that lie in this area have a positive influence on the correlation coefficient. If we multiply two negative values, we also get a positive value. Minus times minus is plus. So all values that lie in this area also have a positive influence on the correlation coefficient. If we multiply a positive value and a negative value, we get a negative value. Minus times plus is minus. So all values that lie in these ranges have a negative influence on the correlation coefficient. Therefore, if our values are predominantly in these two areas, we get a positive correlation coefficient. and thus a positive relationship. If our values are predominantly in these two areas, we get a negative correlation coefficient, and thus a negative relationship. If the points are distributed over all four areas, the positive terms and the negative terms cancel each other out, and we get a very small or no correlation. But now there's one more thing to consider. The correlation coefficient is usually calculated with data taken from a sample. However, we often want to test a hypothesis about the population. In the case of correlation analysis, we then want to know if there is a correlation in the population. For this, we check whether the correlation coefficient in the sample is statistically significantly different from zero. The null hypothesis in the Pearson correlation is the correlation coefficient does not differ significantly from zero. There is no linear relationship. And the alternative hypothesis is the correlation coefficient differs significantly from zero. There is a linear relationship. Attention! It is always tested whether the null hypothesis is rejected or not. In our example, the research question is there a correlation between age and salary in the British population? To find out, we draw a sample and test whether in this sample the correlation coefficient is significantly different from zero. The null hypothesis then is there is no correlation between salary and age in the British population. And the alternative hypothesis, there is a correlation between salary and age in the British population. Whether the correlation coefficient is significantly different from zero based on the sample collected can be checked using a t-test, where R is the correlation coefficient and N is the sample size. A p-value can then be calculated from the test statistic t. If the p-value is smaller than the specified significance level, which is usually 5%, then the null hypothesis is rejected. Otherwise, it is not. But what about the assumptions for a Pearson correlation? Here we must distinguish whether we just want to calculate the Pearson correlation or whether we want to test a hypothesis. To calculate the Pearson correlation coefficient, only two metric variables need to be present. Metric variables are, for example, a person's weight, a person's salary, or electricity consumption. The Pearson correlation coefficient then tells us how large the linear relationship is. If there is a non-linear relationship, we cannot tell from the Pearson correlation coefficient. However, if we want to test whether the Pearson correlation coefficient is significantly different from zero, the two variables must always be normally distributed. If this is not given, the calculated test statistic t or the p-value cannot be interpreted reliably. Let's continue with the Spearman correlation. The Spearman rank correlation is the non-parametric counterpart of the Pearson correlation. But there is an important difference between both correlation coefficients. Spearman correlation does not use the raw data, but the ranks of the data. Let's look at this with an example. We measured the reaction time of 8 computer players and asked their age. When we calculate a Pearson correlation, we simply take the two variables reaction time and age and calculate the Pearson correlation coefficient. However, we now want to calculate the Spearman rank correlation. So first we assign a rank to each person for reaction time and age. The reaction time is already sorted by size. 12 is the smallest value, so gets rank 1. 15, the second smallest value, so gets rank 2, and so on and so forth. We are now doing the same with age. Here we have the smallest value, there the second smallest, there the third smallest, fourth smallest, and so on and so forth. Let's take a look at this in the scatter plot. Here we see the raw data of age and reaction time. But now we would like to use the rankings. So we form ranks from the variables age
and reaction time. Through this transformation, we have now distributed the data more evenly. To calculate the Pearson correlation, we simply calculate the Pearson correlation from the ranks. So, the Spearman correlation is equal to the Pearson correlation, only that the ranks are used instead of the raw values. Let's have a quick look at that in Data tab. Here we have the reaction time and age, and there we have the just created ranks of reaction time and age. Now we can either calculate Spearman correlation of reaction time and age, where we get a correlation of 0.9, or we can calculate Pearson correlation from the ranks, where we also get 0.9, so exactly the same as before. If you like, you can download the dataset. You can find the link in the video description. If there are no rank ties, we can also use this equation to calculate the Pearson correlation. RS is the Spearman correlation, N is the number of cases, and D is the difference in ranks between the two variables. Referring to our example, we get the different D's with this. 1 minus 1 is equal to 0, 2 minus 3 is minus 1, 3 minus 2 is 1, and so on. Now we square the individual D's and add them all up. So the sum of Di squared is 8. N, which is the number of people, is 8. If you put everything in, we get a correlation coefficient of 0.9. Just like the Pearson correlation coefficient R, Spearman correlation coefficient RS also varies between -1 and 1. Let's continue with Candle's tau. Candle's tau is a correlation coefficient and is thus a measure of the relationship between two variables. But what is the difference between Pearson correlation and Candle's rank correlation? In contrast to Pearson correlation, Candle's rank correlation is a non-parametric test procedure. Thus, for the calculation of Candle's tau, the data need not be normally distributed and the variables need only have ordinal scale levels. Exactly the same is true for the Spearman rank correlation, right? That's right! Candle's tau is very similar to Spearman's rank correlation coefficient. However, Candle's tau should be preferred over Spearman's correlation if very few data with many rank ties are available. But how is Candle's tau calculated? We can calculate Candle's tau with this formula, where C is the number of concordant pairs and D is the number of discordant pairs. What are concordant and discordant pairs? We will now go through this with an example. Suppose two doctors are asked to rank 6 patients according to their physical health. One of the two doctors is now defined as a reference and the patients are sorted from 1 to 6. Now the sorted ranks are matched with the ranks of the other doctor. E.g., the patient who is in 3rd place with the reference doctor is in 4th place with the other doctor. Now using Candle's tau, we want to know if there is a correlation between the two rankings. For the calculation of Candle's tau, we only need these ranks. We now look at each individual rank and note whether the values below are smaller or greater than itself. So we start at the first rank 3. 1 is smaller than 3, so gets a minus. 4 is greater, so gets a plus. 2 is smaller, so it gets a minus. 6 is greater, so it gets a plus. And 5 is also greater, so it also gets a plus. Now we do the same for 1. Here, of course, each subsequent rank is greater than 1. So we have a plus everywhere. At rank 4, 2 is smaller and 6 and 5 are greater. Now we do this for rank 2 and rank 6. Then we can easily calculate the number of concordant and discordant pairs. We get the number of concordant pairs by counting all the plus. In our example, we have 11 plus in total. We get the number of discordant pairs by counting through all the minus. In our example,
we have a total of 4 minus. C is thus 11 and D is 4. Candle's tau now is 11 minus 4 divided by 11 plus 4. And we get a candle's tau of 0.47. We get an alternative formula for candle's tau herewith. S is C minus D, therefore 7. N is the number of cases, i.e. 6. If we insert everything, we also get 7 divided by 15. Just like the Pearson correlation coefficient R, candle's tau also varies between -1 and +1. We have again calculated the correlation coefficient using data from a sample. Now we can test if the correlation coefficient is significantly different from 0. Thus, the null hypothesis is the correlation coefficient tau is equal to 0, there is no relationship. And the alternative hypothesis is the correlation coefficient tau is unequal to 0, there is a relationship. Therefore, we want to know if the correlation coefficient is significantly different from 0. You can analyze this either by hand or with a software like DataTab. For the calculation by hand, we can use the set distribution as an approximation. However, for this we should at least have 40 cases, so the 6 cases from our example are actually too few. We get the set value with this formula. Here we have tau, and n is the number of cases. This brings us to the last correlation analysis, the point-by-zero correlation. Point-by-zero correlation is a special case of Pearson correlation and examines the relationship between a dichotomous variable and a metric variable. What is a dichotomous variable and what is a metric variable? A dichotomous variable is a variable with 2 values, for example, gender with male and female, or smoking status with smoker and non-smoker. A metric variable is, for example, the weight of a person, the salary of a person, or the electricity consumption. So, if we have a dichotomous variable and a metric variable, and we want to know if there is a relationship, we can use a point-by-zero correlation. Of course, we need to check the assumptions beforehand, but more about that later. How is the point-by-zero correlation calculated? As stated at the beginning, the point-by-zero correlation is a special case of the Pearson correlation. But how can we calculate the Pearson correlation when a variable is nominal? Let's look at this with an example. Let's say we are interested in investigating the relationship between the number of hours studied for a test and the test result, passed, failed. We've calculated data from a sample of 20 students, where 12 students passed the test and 8 students failed. We have recorded the number of hours each student studied for the test. To calculate the point-by-zero correlation, we first need to convert the test result into numbers. We can assign a score of 1 to students who passed the test and a score of 0 to students who failed the test. Now we can either calculate the Pearson correlation of time and test result, or we use the equation for the point-by-zero correlation. x1 dash is the mean value of the people who have passed, and x2 dash is the mean value of the people who failed. n1 is the number of people who passed, and n2 the number of people who failed, and n is the total number. But whether we calculate the Pearson correlation or we use the equation for the point-by-zero correlation, we get the same result both times. Let's take a quick look at this in DataTab. Here we have the learning hours, the test result with passed and failed, and there the test result with 0 and 1. We define the test result with 0 and 1 as metric. If we now go to correlation and calculate the Pearson correlation for these 2 variables, we get a correlation coefficient of 0.31. If we calculate the point-by-zero correlation for learning hours and exam result with passed and failed, we also get a correlation of 0.31. Just like the Pearson correlation coefficient R, The point biseral correlation coefficient RPB also varies between -1 and 1. If we have a coefficient between -1 and less than 1, there is a negative correlation, thus a negative relationship between the variables. If we have a coefficient between greater than 0 and 1, there is a positive correlation, that is, a positive relationship between the two variables. If the result is 0, we have no correlation. As always, with the point biseral correlation, we can also check whether the correlation coefficient is significantly different from 0. Thus, the null hypothesis is the correlation coefficient R is equal to 0, there is no relationship, and the alternative hypothesis is the correlation coefficient R is unequal to 0, there is a relationship. Before we get to the assumptions, here's an interesting note. When we compute a point biseral correlation, we get the same p-value as when we compute a t-test for independent samples for the same data. So, whether we test a correlation hypothesis with the point biseral correlation or a difference hypothesis with the t-test, we get the same p-value. Now, if we compute a t-test in data tab with these data and we have the null hypothesis, there is no difference between the groups failed and passed in terms of the variable learning hours, we get a p-value of 0.179. And also, if we calculate a point biseral correlation and have the null hypothesis, there is no correlation between learning hours and test result, we get a p-value of 0.179. In our example, the p-value is greater than 0.05, which is most often used as a significance level, and thus the null hypothesis is not rejected. But what about the assumptions for a point biseral correlation? Here we must distinguish whether we just want to calculate the correlation coefficient or whether we want to test a hypothesis. To calculate the correlation coefficient, only one metric variable and one dichotomous variable must be present. However, if we want to test whether the correlation coefficient is significantly different from 0, the one metric variable must also be normally distributed. If this is not given, the calculated test statistic t, or the p-value, cannot be interpreted reliably. This brings us to the last question. What is causality? And what is the difference between causality and correlation? Causality is the relationship between a cause and an effect. In a causal relationship, we have a cause and a resultant effect. An example: coffee contains caffeine, a stimulating substance. When you drink coffee, the caffeine enters the body, affects the central nervous system, and leads to increased alertedness. Drinking coffee is the cause of the feeling of alertedness that comes afterwards. Without drinking coffee, the effect, i.e. the feeling of alertedness, would not occur. But causality is not always so easy to determine. Clear requirements must be met in order to speak of a causal relationship. But more about that later. So, what is the difference between correlation and causality? A correlation tells us that there is a relationship between two variables. Example: there is a positive correlation between ice cream sales and the number of sunburns. However, an existing correlation cannot tell us which variable influences which, or whether a third variable is responsible for the correlation. In our example, both variables are influenced by a common cause, namely sunny weather. On sunny days, people buy more ice cream and spend more time outdoors. This can lead to an increased risk of sunburns. Causality means that there is a clear cause-effect relationship between two variables. Causality exists when you can say with certainty which variable influences which. However, a common mistake in the interpretation of statistics is that a correlation is immediately assumed to be a causal relationship. Here is an example. The American statistician Darrell Huff found a negative correlation between the number of head lice and the body temperature of the inhabitants of an island. A negative correlation means that people with many head lice generally have a lower body temperature and people with few head lice generally have a higher body temperature. The islanders concluded that head lice were good for health because they reduced fever. So their assumption was that head lice have an effect on the temperature of the body. In reality, the correct conclusion is the other way around. In an experiment, it was possible to prove that high fever drives away the lice. So the high body temperature is the cause, not the effect. What are the conditions for talking about causality? There are two conditions for causality. Number one, there is a significant correlation between the variables. This is easy to check. We simply check whether the correlation coefficient is significantly different from 0. Number two, the second condition can be met in 3 ways. First, chronological sequence. There is a chronological sequence and the results of one variable occurred before the results of the other variable. Second, experiment. A controlled experiment was conducted in which the 2 variables can be specifically influenced. And number 3, theory. There is a well-founded and plausible theory in which direction the causal relationship goes. If there is only a significant correlation, but none of the other 3 conditions are met, we can only speak of correlation, never of causality. After examining how correlation analysis helps us determine the extent to which variables are related, we now move into the field of regression. Regression analysis allows us to understand the nature of the relationship more deeply and make predictions. Let's look at how we can use simple linear regression to predict values and explore how this extends into multiple regression, offering even richer insights into complex data interactions.
After watching this video, you will know what regression analysis is and what the differences between simple and multiple linear regression are. Further, you will be able to interpret your results, understand the assumptions for a linear regression, and also the use of dummy variables. And at the end, I explain to you the basics about logistic regression. And of course, I'll also show you how to calculate a regression easily online. Let's get started. A regression analysis allows you to infer or predict a variable based on one or more other variables. Let's say you want to find out what influences the salary of people. For example, you could take the highest level of education, the weekly working hours, and the age of people. Now you can investigate whether these 3 variables have an influence on the salary. If you can do so, you can predict a person's salary by taking the highest educational level, the weekly working hours, and a person's age. The variable you want to infer, the one that you want to predict, is also called the dependent variable or criterion. The variables you use for your prediction are called independent variables or predictors. Regression analysis can be used to achieve 2 goals. First, you can measure the influence of one variable or several variables on another variable, or you can predict a variable based on other variables. This is the second goal. In order to give you a feeling for this, let's go through some examples now. Let's start by measuring the influence of one or more variables on another. In the context of your research work, you might be interested in what has an influence on children's ability to concentrate. You're interested in whether you can prove that there are parameters that positively or negatively influence children's ability to concentrate. But in this case, you're not interested in predicting children's ability to concentrate. Another example would be you could investigate whether the educational level of parents and the place of residence have an influence on the future educational level of children. This area is very research-based and has a lot of application in the social and economic sciences. The second area, which is using regressions for predictions, is more application-oriented. Let's say in order to get the most out of hospital occupancy, you might be interested in how long a patient will stay in the hospital. So based on the characteristics of the prospective patient, such as age, reason for stay, and pre-existing conditions, you want to know how long this person is likely to stay in the hospital. Based on this prediction, you can, for example, optimize bed planning. Another example would be that as an operator of an online store, you may be very interested in which product a person is most likely to buy. So you want to suggest this product to the visitor in order to increase the sales of the online store. This is where regression comes into play. What we now need to know is that there are different types of regression analysis, and we get started with these types right now. In regression analysis, a distinction is made between simple linear, multiple linear, and logistic regression. In simple linear regression, you use only one independent variable to infer the dependent variable. In the example where we want to predict the salary of people, we use only one variable, either, for example, if a person has studied or not, the weekly working hours, or the age of a person. In multiple linear regression, we use several independent variables to infer our dependent variable. So we use the highest educational level, weekly working hours, and the age of a person. So therefore, the difference between a simple and a multiple regression is that in one case we only use one independent variable, and in the other case we use several independent variables. Both cases have in common that the dependent variable is metric, and metric variables are, for example, the salary of a person, the body size, the shoe size, or, for example, the electricity consumption. In contrast to that, logistic regression is used when you have a categorical dependent variable. So, for example, when you want to infer whether a person is at high risk of burnout or not. Whenever yes and no answers are possible, you use a logistic regression. So in linear regression, the dependent variable is metric. In logistic regression, it is categorical. Whenever the dependent variable is yes or no, you will use a logistic regression. Does one person buy a product, yes or no? Is a person healthy or sick? Does a person vote for a certain party, yes or no? And so on and so forth. In all these cases, it does not matter what scale level the independent variables have. They can be either nominal, ordinal, or metric. So as I just said, the scale level of the dependent variable can be metric, ordinal, or nominal in all three cases. So in the simple linear, in the multiple linear, and in a logistic regression. The dependent variable is metric in the linear case, and it is nominal or ordinal in the case of a logistic regression. It is important to know that in the case of a nominal or an ordinal independent variable, the variables may classically have only two characteristics, such as gender with male and female. If your variables have more than two characteristics, then you have to form so-called dummy variables. But we will talk about dummy variables a bit later. So now a quick recap for you. There is the simple linear regression, and the question could be, does the weekly working time have an impact on the hourly wage of people? The distinguishing point is that we have only one independent variable in this case. Then there is the multiple linear regression. A question could be, do the weekly working hours and the age of employees have an influence on the hourly wage? In this case, we have at least two independent variables, so for example, weekly working hours and age. And now let's look at the last case, which is logistic regression. Here the question could be, do the weekly working hours and the age of employees have an influence on the probability that they are at risk of burnout? In this case, burnout at risk has the expressions yes or no. So now I hope you got a first impression about what regression analysis is, and we'll move on to the linear regression now. Let's get started. As you already know, a regression analysis allows you to infer or predict a variable based on one or more other variables. But what is the difference between a simple linear regression and a multiple linear regression? The simple linear regression uses only one independent variable to infer the dependent variable. So for example, does the weekly working time have an influence on the hourly salary of employees? In a multiple linear regression, several independent variables are used to infer the dependent variable. So for example, do the weekly working hours and the age of employees have an influence on their hourly salary? So therefore, the difference between a simple regression and a multiple regression is that in one case, only one independent variable is used, and in the other case, we use several independent variables. So both have in common that the dependent variable is metric. In contrast, logistic regression is used when you have a categorical dependent variable. Logistic regression is discussed later in this video. Let's first start with the simple linear regression. The goal of a simple linear regression is to predict the value of a dependent variable based on an independent variable. The greater the linear relationship between the independent variable and the dependent variable is, the more accurate is the prediction. Visually, the relationship between the variables can be represented in a scatter plot. The greater the linear relationship between the dependent and the independent variable, the more the data points lie on a straight line. The task of a simple linear regression is now to determine exactly the straight line that best describes the relationship between the dependent and the independent variable. In the context of a linear regression analysis, a straight line is plotted on the scatter plot. In order to determine the straight line, the linear regression uses the method of least squares. Let's say a hospital asks you to give them an estimate based on the age of a person, how long this person will stay in the hospital after a surgery. The target of the hospital operator is to optimize the bed planning. In this example, your dependent variable, the one you want to infer, is the length of stay after surgery. Your independent variable is the age of a person. The equation that describes the model now looks like this. B is the slope and A is the receptor point. If a person would be 0 years old, which doesn't really make sense in this example, the model would tell us that this person stays A days in the hospital. In order to calculate the coefficients, the hospital must of course provide you with a sample of people where you know the age and the length of stay after surgery. By using your data, you could find out that B is 0.14 and A is 1.2. This is now our model, which helps us to estimate the length of stay after surgery based on the age of people. Now let's say a person who is 33 years old is registered for a surgery. Then we would put 33 for X. Our model then tells us that this person stays in the hospital for 5.82 days after surgery. Now, of course, the question is, how do you calculate the slope B and how do you calculate the intercept A? Usually, you use a statistics program like DataTab. In the case of simple linear regression, however, it is also quite simple to do this by hand. B results from the correlation of the two variables times the standard deviation of the variable length of stay after surgery divided by the standard deviation of age. A is obtained by calculating the mean value of the length of stay minus the slope times the mean value of the age. The regression line always tries to map the given data with a straight line as best as possible. Of course, this always results in an error. This error is called epsilon. Let's say we estimate the length of stay after surgery of a person who is 33 years old. Our model tells us that the person stays in the hospital for 5.82 days, but in fact, he or she stays in the hospital for 7 days. Then the difference between the estimated value and the true value is our error, and exactly the error epsilon. Now you have a good overview of what a simple linear regression is, and we proceed with the multiple linear regression now. Unlike simple linear regression, multiple linear regression allows for the consideration of more than two independent variables. As we already know, the goal of a regression is to estimate one variable based on several other variables. The variable to be estimated is called the dependent variable or criterion. The variables that are used for prediction are called independent variables or predictors. Multiple linear regression can be used to control for the influence of a third-party variable. Multiple linear regression is often used in empirical social research as well as in market research. In both areas, it is of interest to find out what influence different factors have on a certain variable. Therefore, the equation for a simple linear regression looks like this. We have one independent variable x plus the constant. If we now go the way of multiple linear regression, we have several independent variables. The first variable, the second variable, and the kth variable. The coefficients can now be interpreted similarly to the linear regression equation. If all independent variables are 0, we get the value a. If an independent variable changes by 1 unit, the corresponding coefficient b indicates by how much the dependent variable changes. Let's say x1 is the age of a person and b1 is 10. Then for every further year, y is increased by 10. If the person is 5, we have 5 times 10, which equals 50, so y is increased by 50. Before we now look at the interpretation of the regression results, I will first explain to you how you can easily calculate a linear regression online. In order to do this, simply visit Data tab. You can find the link in the video description and just copy your own data into this table. Then you simply click on the Regression tab. After you've copied your data into the upper table, your variables will appear here below. Now you only need to select your dependent variable and one or more independent variables. Of course, this dataset is far too small, but it just serves us as an example. Your own dataset may of course have several thousand rows. Let's say we want to find out what influences a person's salary, so we choose salary as the dependent variable. As the independent variables, we can now choose gender, age, and for example, weight. As soon as you've selected the variables you want to use, Data tab calculates a regression analysis for you. Since your dependent variable has a matrix scale level, a linear regression is calculated. Now you can see the results here. We will go through the interpretation of the results in detail in a moment. The good thing is the Data tab also helps you with the interpretation. So just click here. A multiple linear regression analysis was performed to examine whether male, age or weight variables significantly predict salary. The regression model indicated that the predictors explained 48.99% of the variance, and a collective significant effect was not found. F equals 2.56, P equals 0.1, and R squared is 0.49. But let's now go into more detail about the interpretation of results. Your results will be presented to you in this form. You can now, of course, just use the interpretation in words on Data tab, but we'll go through each block individually. Let's start with the model summary. The multiple correlation coefficient R measures the correlation between the dependent variable and the combination of the independent variables. What does that mean? Here we see the equation for linear regression. Our statistics program, like DataTab, calculates the regression coefficients. Now you can sum up all the values, and with the summed values you can calculate the correlation with the dependent variable. This correlation is the multiple correlation coefficient R. Or to say it in other words, with the regression coefficients and the independent variables, an estimate of the dependent variable is calculated. R now indicates how strong the correlation is between the true dependent variable and the estimated variable. Therefore, the greater the correlation, the better the regression model. The coefficient of determination R squared indicates how much the variance of the dependent variable can be explained by the independent variables. Your dependent variable has a certain variance. The more of this variance we can explain, the better it is. Let's take the example of how long you stay in the hospital after surgery. Of course, not every person stays in the hospital for the same amount of time, so we have a variation, and it's this variation that we want to explain with the help of a regression model. If, for example, we can predict the length of stay in hospital very well with the age and the type of surgery, this R squared is very large. If we can even explain everything, the result would be 1. In this case, we could predict exactly how long a person will stay in the hospital after a surgery using only the age and the type of operation, and we can explain all the variance of the dependent variable. But of course, that doesn't happen very often in practice. R squared overestimates the coefficients of determination when too many independent variables are used. To fix this issue, the adjusted R square is often calculated. The standard estimation error indicates by how much the model overestimates the dependent variable on average. Let's say you want to predict the length of stay in days after surgery. If your standard estimation error, for example, is 4, this would mean that you miscalculate on average by 4 days with your prediction. Now, of course, your question to the hospital management would be whether an average deviation of 4 days is too much, or whether the hospital says, great, this enables us a much better planning security. So next, this table is displayed. Here, the so-called F-test is calculated. The F-test tests the null hypothesis whether the variance explanation R squared in a population is 0. This test is often not of great interest. The test is equivalent to asserting that all true slope coefficients in a population are 0. So B1 is 0, B2 is 0, and up to Bk is 0. In this case, since we have a very small data set in our example, the results show that the null hypothesis cannot be rejected. The p-value is greater than 0.05, and we assume, based on available data, that all coefficients are 0. So now we reach the probably most interesting table. Here we see the unstandardized coefficients, the standardized coefficients, and the significance level. Capital B, the unstandardized coefficients, are just the coefficients that you can put into your regression equation. So if we want to predict the salary, we have a constant of 1920, plus the value of the gender variable, plus the value for the age variable, plus weight. This allows us to use the unstandardized regression coefficients to build our regression model. If we want to predict the salary, we now only have to insert the variables. Beta are the standardized coefficients. Here you can see which variable has the greatest influence on the salary. In this case, age has the greatest influence on salary because beta of age has the greatest amount. And finally, we see the significance value for the coefficients. Values smaller than 0.05 are considered significant. In this case, we see that not a single coefficient is significant. What does that mean now? The null hypothesis in each case is that these coefficients are zero in the population. If the p-value is greater than 0.05, we cannot reject this null hypothesis based on the available data. And thus, it is assumed that the coefficients in the population are not different from zero, and therefore the variables have no influence on salary. Due to the fact that I've used a data set that is actually very small, it's difficult to reach significant values. Of course, when calculating a regression analysis, you also have to check the assumptions. If the assumptions are not fulfilled, you cannot interpret the results of the regression meaningfully. Therefore, we now take a look at the assumptions. The assumptions for the linear regression are as follows. There must be a linear relationship between the dependent and the independent variables. The error epsilon must be normally distributed. Third assumption is that there must be no multicollinearity or no instability of the regression coefficients. And finally, there must not be heteroscedasticity. The variance of the residuals must be constant over the predicted values. And now we'll go into each point in more detail. Let's get started. In a linear regression, a straight line is drawn through the data. This straight line should represent all points as good as possible. If the points are non-linear, the straight line cannot fulfill this task. Let's look at these two graphs. In the first one, we see a nice linear relationship between the dependent and the independent variable. Here, the regression line can be drawn in a meaningful way. In the second case, however, we see that there is a clearly non-linear relationship between the dependent and the independent variable. Therefore, it's not possible to put the regression line meaningfully through the points. Since this is not possible, the coefficients of the regression model cannot be interpreted meaningfully, or errors in the prediction can occur that are larger than expected. Therefore, we have to check at the beginning whether there is a linear relationship between the dependent and the independent variables. This is usually done graphically. The next requirement is that the error epsilon must be normally distributed. In order to check this, there are two ways. One is the analytical way and the other one is the graphical way. When using the analytical way, you can use either the Kolmogorov-Smirnov test or the Shapiro-Wilk test. If the p-value is greater than 0.05, there is no deviation of the data from the normal distribution, so it can be assumed that your data are normally distributed. However, these analytical tests are not used that often anymore because they tend to always attest normal distribution in small samples and they become significant very quickly in larger samples, thus rejecting the null hypothesis that the data is normally distributed. Therefore, the graphical version is used more and more. For the graphical solution, you can either look at the histogram or better, the QQ plot. The more your data lies on the line, the better is the normal distribution. And now we come to the heteroscedasticity. Another assumption for the linear regression is that the residuals have a constant variance. Since your regression model never exactly predicts your dependent variable in practice, you always have a certain error. Now you can plot your dependent variable on the x-axis and the error on the y-axis. The error should scatter evenly over the whole range. then homoscedasticity is present. However, if the results look like this, then we have heteroscedasticity. In this case, we have different error variances depending on the value range of the dependent variable. This should not be the case. And before I show you how you can check the assumptions online, we now come to the last assumption, which is no multicollinearity. Multicollinearity means that two or more independent variables are strongly correlated with each other. The problem with multicollinearity is that the effect of individual variables cannot be clearly separated. Let's look at the regression equation again. There we have the dependent variable and here the independent variables with the respective coefficients. So now, for example, if there is a high correlation between x1 and x2, or if these two variables are almost equal, then it is difficult to determine b1 and b2. If both are completely equal, the regression model does not know what b1 and b2 should be. This means that the regression model becomes unstable. If you want to use the regression model for a prediction, it does not matter whether there is multicollinearity or not. In a prediction, you're only interested in how good the prediction is, but you're not interested in how big the influence of the respective variables is. However, if the regression model is used to measure the influence of the independent variable on the dependent variable, there must not be multicollinearity. And if there is, the coefficients cannot be interpreted meaningfully. So now the question is, how can we diagnose multicollinearity? If we look at the regression equation again, we have the variables x1, x2, up to the variable xk. We now want to know if x1 is quite identical to another variable or a combination of the other variables. In order to do this, we simply set up a new regression model. In this new regression model, we take x1 as the new dependent variable. If we can now predict x1 very well by using the other independent variables, we don't need x1 anymore because we can use the other variables instead. If we would now use all variables, it could be that the regression model is unstable. In mathematics, we say that the equation is overdetermined. We can now do this for all other variables. So we estimate now x2 by using the other independent variables, and we estimate xk by using the other independent variables. For all k regressions, in this case we have k new regression models, we calculate the so-called tolerance or the VIF value. The tolerance is obtained by taking 1 minus r squared, which is the variance explanation. Once again, the variance explanation indicates how much of the variance of x1 can be explained by the other variables. The more it is, the more one speaks of multicollinearity. If these variables can explain 100% of the variance of x1, then we no longer need x1 in the upper equation. If the tolerance is less than 0.1, you have to be careful, because in this case we could have multicollinearity. On the other hand, we have the VIF value. The VIF value is calculated by dividing 1 by the tolerance. Accordingly, you have to be careful if the values are greater than 10. And now I will show you how you can test the assumptions online. If you want to test the assumptions online with DataTab, you only need to select your variables and then click on Check Assumptions. Now you see a nice overview of the results here. You can check the linearity, the normal distribution of the error, the multicollinearity, and the heteroscedasticity. It's very simple, just try it yourself. Now it's time to look at dummy variables. You have to use dummy variables if you want to use categorical variables with more than 2 values as your independent variables. As independent variables or predictors, either metric or categorical variables with 2 expressions can be used. Of course, it's also possible to use variables with more than 2 categories, and I will explain this to you in the next slides. Categorical variables with 2 characteristics are also called dichotomous. An example would be gender with the categories male and female. Let's say you coded female as 0 and male as 1. In this case, female would be the reference category. If we now look at the regression equation and say the variable x1 is gender, then b1 is the regression coefficient for gender. Now, how can we interpret b1? We said 0 is female and 1 is male, so we just put that in. Then we have 0 times b1 for a female person and 1 times b1 for a male person. Accordingly, b1 indicates the difference between male and female. Let's say we want to predict the income of a person, so y is the income. If a person is male, this person earns more by the amount of b1 than a woman. If the person is male, there is a 1 here and we have 1 times this value. If the person is female, there is a 0 here and we have 0 times this value. If b1 is 400, for example, then it means that men earn 400 euros more than women according to this model. Now we've discussed how to handle variables with 2 values. Further, we should look at what we do when we have a variable with more than 2 values or categories. Let's say you want to predict the fuel consumption of a car based on its horsepower and the vehicle type. And let's say there are only 3 vehicle types: sedan, sports car and family van. Thus, here we have a variable vehicle type with more than 2 characteristics, but for a regression model, we need a categorical variable with 2 characteristics. Therefore, the question is now, what should we do next? In order to use categorical variables in a regression, we have to create dummy variables. This means that we simply create 3 new variables. Each new variable has 2 characteristics. These characteristics are 0 and 1, or yes or no. So here we have our vehicle type with the characteristics sedan, sports car and family van. Now we create 1 new variable for each characteristic. So first we create the variable, is it a sedan, yes or no. Second would be, is it a sports car, yes or no. And our third variable asks, is it a family van, yes or no. So before we had 1 variable and now we got 3 variables which are dichotomous and therefore they all have only 2 characteristics. And these 3 new variables can now be used in the regression model. So the next question is now, what does that mean for the data preparation? You originally have 1 column with the vehicle type where the individual vehicles from your sample are listed. The first is a sedan, the second is also a sedan, the third is a sports car, and so on and so forth. Out of this table, you create your 3 new variables. What is the first car? A sedan, so you put a 1 here and a 0 for the others. It's not a sports car and it's not a family van. The second one is also a sedan, so we'll put a 1 here again. And the third one is a sports car, so we'll put a 1 here and the others are 0. By continuing this procedure, we have finally created our new dummy variables. Now there's only one important thing to note. The number of dummy variables is always the number of characteristics minus 1. Why is that the case? If we know that it is a sedan, we are sure that it's not a family van. If we know that it is a sports car, we can also be sure that it's not a family van. And if it's not a sedan and not a sports car, we can be sure that it is a family van. Accordingly, one of the three variables is not needed because this information is redundant. Therefore, n-1 dummy variables are created. So in this case, we only need the dummy variable, is it a sedan or is it a sports car? Of course, you can also drop sedan and use the other two. And now I'll show you how you can create the dummy variables online with Data tab. In this example, we use salary as our dependent variable and as independent variable the age and the company. The variable company here has three characteristics: BMW, Ford and GM. Now we can see that Data tab automatically creates the dummy variables. Once we have the age and once the new dummy variables, is it BMW and is it Ford? Since we only need n-1 dummy variables, the last category was dropped. If your dependent variable is categorical, then you need the logistic regression. And logistic regression is what we are going to look at now. In the previous part, we discussed linear regression. In a linear regression, the dependent variable is metric. For example, it could be salary or height. Now let's look at the logistic regression. Here the dependent variable is a categorical variable. Let's say you want to predict whether a person is at risk for burnout or not. You want to make this prediction by asking a person's highest educational attainment, weekly working hours, and the person's age. Since the variable whether a person is at risk for burnout or not is a categorical variable, you have to use a logistic regression. The logistic regression is a special case of regression analysis, and it is calculated when the dependent variable is nominally or ordinally scaled. Let's look at a few examples first. For an online retailer, you need to predict which product a particular customer is most likely to buy. In order to do this, you receive a data set with past visitors and their purchases from the online retailer. In this case, you need a logistic regression because your dependent variable is a categorical variable, namely, which product is a particular customer most likely to buy. The second example comes from the medical area. You want to investigate whether a person is susceptible to a certain disease or not. For this purpose, you receive a data set with deceased and non-deceased people, as well as other medical parameters. Again, in this case, you need a logistic regression because the dependent variable is categorical and it asks, is a person susceptible to a particular disease or not? And the last example comes from politics. The question could be, would a person vote for party A if there were elections next weekend? So again, a categorical dependent variable with yes and no as response options. What is logistic regression now? In the basic form of logistic regression, dichotomous variables, that is, variables with the characteristics 0 and 1, or yes or no, can be predicted. For this purpose, the probability of occurrence of characteristic 1, which is characteristic present, is estimated. In medicine, for example, a common goal is to find out which variables have an impact on a disease. In this case, 0 could be not deceased and 1 deceased. And the influence of age, gender, and for example, smoking status on this particular disease could be examined. Let's look at this in a graphical way. So we have our independent variables age, gender, and smoking status, and we use these three variables in order to predict whether a person is likely to get a certain disease or not. So the dependent variable is, will the person get a disease or not? So maybe now you might ask yourself the question, and why do I need a logistic regression for this? Why can't I just use a linear regression? A quick recap. In a linear regression, this is our regression equation. Now we have a dependent variable that is 0 or 1. Therefore, no matter what value we have in a dependent variables, we always get either 0 or 1. If we are using a linear regression, we would simply put a linear straight line into these points. The graph shows that values between plus and minus infinity can now occur. The goal of logistic regression is to estimate the probability of occurrence, not the value of the variable itself. So we want to know how likely it is that a value of 1 will be the result of the given values for our independent variables. The range of values for the prediction is thus restricted to the range of 0 to 1. In order to ensure that only values between 0 and 1 are possible, the logistic function is used. The logistic model is based on the logistic function. The important thing about the logistic function is that only values between 0 and 1 are possible. So no matter where we are here on the x-axis, between minus and plus infinity, we can only get values between 0 and 1 as a result. And that is exactly what we want. The equation for logistic regression now looks like this. We have 1 divided by 1 plus e to the power of minus z. For z, we now use the usual equation from the linear regression, which is the equation here below. b1 to bk are the regression coefficients, and a is the on point, x1 to xk are the independent variables. After we insert all that, our logistic function looks like this. Now we need to determine the coefficients so that our model best represents the given data. In order to solve this problem, we use the so-called maximum likelihood method. There are good numerical solutions that help us solve the problem. So usually we just use a statistics program and it will give us the values b1, b2 up to bk. Finally, I will now show you how to calculate a logistic regression online with DataTab. In order to do this, you just visit datatab.net and you copy your own data into this table. When you select a categorical dependent variable, a logistic regression is automatically calculated. Let's say your dependent variable is a person buys a product or not, with the expressions yes and no, and the independent variables are salary and age. After you click on the variables, a logistic regression is automatically calculated. And now you get the results, which you can see below. The first table is the so-called classification table. This table tells us how well we can classify the categories with the regression model. After that, we get the model summary and the coefficients.
We just talked about regression, where we predict values based on known relationships. Let's now shift our focus to discovering hidden patterns in data with no apparent relationship. This brings us to cluster analysis, especially the k-means clustering technique. K-means clustering is a powerful method used to identify hidden groups or clusters within our data. Let's explore how that works and how it can enhance our understanding of complex datasets.
In this video, I will explain to you everything you need to know about cluster analysis. I will start with the question, what is the k-mean cluster? And then I will show you how you can easily calculate it online with DataTab. And now let's start with the question, what is the k-means cluster analysis? The k-means cluster analysis is one of the simplest and most common methods for cluster analysis. By using the k-means method, you can cluster your data by a given number of clusters. So you already need to define beforehand the number of clusters. For example, you have a dataset and you want to cluster your cases into 3 clusters. This can be done with the k-means cluster analysis. For example, you could have a dataset with 15 European countries and you want to cluster them into 3 country groups. So now the question is, how does the k-means cluster analysis work? There are 5 simple steps required. Let's start with the first step. First, you have to define the number of clusters to find the groups or clusters. The number of clusters is the k in k-means. In our case, we simply select 3 clusters, so in this example k was selected equal to 3. The second step now is to set the cluster centers random. Each of the centers now represents 1 cluster. Let's come to step 3. Now we have selected the number of clusters and we set the cluster centers randomly. Now we assign each element to 1 cluster. So for example, we assign each country to 1 cluster. Let's start with 1 element, and now the distance from the first element to each of the cluster centroids is calculated. So for example, we calculate the distance from this element to each cluster centroid. Afterwards, each element is assigned to the cluster to which it has the smallest distance. In our example, the distance between this element and the cluster centroid is the smallest. So we will assign this element to the yellow cluster. Now this step is repeated for all further elements. So at the end we have 1 yellow cluster, 1 red cluster and 1 green cluster, and then all points are initially assigned to a cluster. So let's summarize it again. We first have defined the number of clusters, we have then assigned the cluster centroid randomly, and we have assigned each element. In step 4, we now calculate the center of each cluster. So for the green elements, for the yellow elements and for the red elements, the center of each cluster is calculated. These centers are the new cluster centroids now. This means that we simply shift the centroids into the cluster center, so the cluster centroids are moved to the cluster centers now. In step number 5, we assign the elements to the new clusters, since the centroids now can be located at a different element. Each element is assigned to the cluster that is closest to it. Now we have finished all steps, and from now on, step 4 and 5 are repeated until the cluster solution does not change anymore. Then the clustering procedure is over. One disadvantage of the k-means method is that the final results depends very much on which initial clusters we used. To take this into account, the whole procedure is carried out several times, and different randomly chosen starting points are used for each of the calculations. Each time we use different starting points, it could be that the outcome is different. So we do the whole cluster analysis several times in order to get the best possible result. If you use data tab to calculate the cluster analysis, the analysis is, for example, done 10 times with 10 different randomly chosen starting points. And then at the end, the best cluster solution is chosen. So the next question is, what is the optimal cluster number? With each new cluster, the sum distance in the clusters gets smaller and smaller. So if we have a look at this picture where we have 2 clusters and that picture where we have 3 clusters, for sure these 3 clusters fit the data better than these 2 clusters. The distance between the elements and the clusters is in this case higher than in that case. So the question now is, how many clusters should be used? In order to answer this question, we use the elbow method. With each additional cluster, the summed distance between the elements and the cluster center becomes smaller and smaller. However, there is a cluster number from which each additional cluster reduces the sum distance only slightly. This point is used as the number of clusters. So if we have a look at this plot, we can see that there is a big gap between cluster number 1 and 2 and there's also a big gap between the number of clusters 2 and 3, but there's only a small gap between number of clusters 3 and 4. So in this case, we select a number of clusters of 3 clusters. Now I'd like to show you how you can easily calculate a k-means cluster analysis online with DataTab. To do this, please visit datatab.net and click on the Statistics Calculator. In order to calculate a cluster analysis, you simply choose the tab Cluster. If you want to use your own data, you can clear the table and then copy your own data into this table. I will simply use the example data now. So I want to calculate a k-means cluster analysis. Let's say we want to cluster a group of people by salary and age. First, we can define the number of clusters and we enter the number of clusters. DataTab will now calculate everything for you and you get your results right away. So here you can see the 3 clusters with the centroids, and there you can see the elbow method. In this case, the results indicate that we should use a solution with 2 clusters. We have selected 3 clusters before, so we can change it in order to get the best suitable number of clusters. But let's go through the results now step by step. Here we can see how many elements are assigned to the different clusters. And here we get the plot with the different clusters. Here we can see one cluster, we see one cluster there, and we see another cluster here. Further, we get a table where each element is allocated to a cluster. If we now choose 2 as the number of clusters, we get new results and we can see them here. In this plot, we have one cluster here and one cluster there. Moreover, we can see that the 2 clusters fit the data quite well.
Thanks for watching and I hope you enjoyed our video. Don't forget to subscribe our channel.